Is it okay?
Yeah, it's coming.
Okay.
Yes.
Good. Okay.
Yeah, now it is fine.
Mhm. Yeah, these network things are always the problem. Yes, I mean, there are lots of good parts about all these all these things, but yes, it comes with this problem with the network. Yes. So BLSP talks on what?
Data science and
Oh, I see. Okay.
He has written a book, no, on data.
Yes. They had written a book. Yes, exactly.
Sadiq sir,
Yes.
now we can start today's our program.
Which student is given the assignment to introduce chair? Hello? Anyone is here? Okay. Let us start the session without wasting the time. In fact, Professor Patagal is known to everyone. He's a great professor from Pune, University of Pune, and he's always with us and always with the whatever the academic events in research level events in statistics. Is well known to all the delegates. He is an expert in the area of reliability, and he has published several papers as well as books. And recently also he published a book. I'm very much glad to invite you, Professor, to chair the session and do the needful for further proceedings.
Okay, thank you, Satish.
Yeah, Professor. Okay.
Thank you, Professor Satish, for nice introduction. Today there are good morning to all of you, and it's the first session of the second day of the conference, and there are two speakers in the first session. First one is Professor Debashish Kundu from IIT Kanpur. Second one is Somesh Kumar from IIT Kharagpur. Both are from IIT. First, I introduce very briefly. You know all very well. Debashish Kundu is very well known, and we met several places, and he visited our Pune University several times also, and we used to meet every time, at least once in a year in the conferences. I just give you a brief introduction. He's a professor in the Department of Mathematics and Statistics, IIT Kanpur. He did BStat and STAT from ISI Calcutta, PhD from Penn State University. He's a student of Professor C.R. Rao. He's a research in interest, reliability, surveillances, distribution theory, statistical signal processing, worked as a visiting professor at several universities at abroad. He received a lot of awards. Fellow of Royal Statistical Society, London, Fellow of National Academy of Sciences, Fellow of ISPS, and he gave several invited plenary keynote talk in national and international conferences. He has more than 20 PhD students guided. He is chief editor, associate editor, editorial board member in several international journals. He has written 5 books and more than 350 research publications in several international refereed journals. Now over to Professor Kundu, Debashish Kundu.
Okay, thank you, David, for your kind introduction. Yes, I mean, we know David, I think, more than 25 years.
Yeah.
It is always really nice meeting him. And most of the time it is some conference or the other. And now it is because of this e-conference, we are meeting through these e-meetings are happening. So, okay, so let me start my presentation. I hope you can see my presentation. Okay?
Yes.
Okay.
Yeah.
Okay. So,
Fine.
okay,
Okay.
yeah, the way it looks like, I mean, it might get disconnected in between, so I have to reconnect. Okay, so I think you have to bear with it. It
Okay.
is, yeah. So it is not my fault. It is the Airtel's fault. Okay, so let me start. Okay, so my special thanks to Satish also. I mean, he never forgets inviting me, and so thank you, Satish, once more.
Thank you,
It is
Professor. Thank you.
really pleasure attending this one. I think the last one I could not attend because that time I was busy with my one of my personal thing. My daughter was getting married, so I told Satish that I will not be able to present. So yes, thank you, Satish, once more. Okay, so that the presentation is on the bivariate semi-parametric model, and mainly I'll be talking about the Bayesian inference. And currently, for the last couple of years, we are working on this one, and it turns out to be a couple of interesting problems which are there. Okay, so this is more or less about the outline of my talk. I mean, first I will start with the motivations from where this particular problem has arisen. And then I'll be talking about briefly about one of the famous model, which is the Marshall-Olkin bivariate exponential model, which is there for quite some time in the statistical literature. And then will be proposed. Then we'll mention about our proposed model, the bivariate proportional hazard class. Although we had proposed this model some time back, but I think the main contribution of the present work is that we will be mainly talking about the semi-parametric setup. Okay, so which basically makes it more general than the any specific parametric setup, and that is the reason actually this semi-parametric approach. And then since we are talking about the Bayesian one, so we'll be mainly talking about the priors and the associated posterior analysis, and then I'll be talking about the data analysis, what from where the problem has taken place. Okay, I hope everybody can hear me. Is that okay?
Yes, we can hear you.
Very good. Yeah. Okay. Good. Yeah, I just want to make sure in between, because once it happened, I think in one of this one, I keep on saying, and after the end of 1 hour, it realized that nobody could hear anything. Yeah. So anyway, so but before progressing, I would say this one that part of this work, it was with one of my ex-student. Currently, he is a faculty member in the Alia University, Devashish Samanto, and part of this work has appeared on this particular journal. Okay, I mention mainly the problem what we have discussed in this paper, but currently we are working some of the more generalized version. So I'll be talking about those things also. Okay, so now let's see what is the
അല്ല അത് എത്രേ ഉള്ളൂ, ഇല്ല ഇല്ല ഇല്ല. ലിങ്ക്ഡിൻ ഉണ്ട്, ലിങ്ക്ഡിൻ അയച്ചിട്ടുണ്ട്. പ്രവീർ കുമാർ ദാസിന്റെ. ഓക്കെ അയക്കാം.
particular eye condition is that at the beginning it is not detectable, but it is being detected usually quite late, and then the patient becomes blind. Okay, so that is, I think, one of the major concern. So there are lots of. I mean, from the clinical point of view, there are lots of work which is going on for the last many years, and several treatments have been proposed, but apparently none of them are quite successful. So one of the treatment which has been proposed relatively recently. They call the laser treatment. Okay, so basically this experiment, which has been done to see whether the laser treatment has any effect, has any significant effect or not compared to the normal treatment or without any treatment. Okay, so that is basically the whole purpose of this experiment. And the way it has been done, it is basically the patients, they have been chosen. I mean that those who have this particular condition on the eye. So those patients, those who have been chosen, those who come for the clinic. So each patient's the one of the eyes have been chosen at random. Okay, so in that particular eye, the laser treatment has been given, and in the other eye, no treatment has been given. Okay, or sometimes a traditional treatment. Okay, so now the observations are like this, that from the date the treatment has started, from that date till the onset of blindness. Okay, that's what it is. So that is basically the data what we have in these two data sets. Okay, but the difference of the two data sets is that, okay, I'll explain. So yes, for the first data set, which is the data set 1, so we have basically a bivariate data. Okay, where we can see this one, the two variables x and y. X can be left on the right eye because, as I had mentioned, that one of the eye has been chosen at random and the laser treatment has been given. So x basically the time to blindness. Okay, the minimum time to blindness for the laser treated eye, and for the other eye it is a y. Okay, so basically in this particular case you have two variables, x and y. Okay, but one of the major observations, what we have observed, that the data are heavily censored. Okay, so that is one of the major concern. And of course, yeah, I think I should mention it here. There are lots of covariates for each patients, particularly age, sex, and the condition of the eye. In the sense, because this they categorized the condition of the eye from 1 to 7. Okay, so they put it, the worst one is 7 and the best one is 1. So the conditions of the eye, which are also there, and yeah, I think these are the main three covariates which are present. But in this present study, what I'm going to present it today, I'm not going to use the covariates at all. That work is going on now. So I'll be talking about all the things what I'll be talking about, which are without covariates. But at the end, I'll just briefly mention that when the covariates are there, how the things can be taken care of. Okay. Yes, and so these are the major findings. I mean, these are the major observations, descriptions about the data set 1. So there are total 197 observations. That means 197 patients, and you can see that, as I had mentioned, the data are heavily censored. So only 38 observations are complete. Okay, so you can see this one there. So rest of the observations are censored some way or the other. So now, since you have both the variables x and y, so it can be censored in one observations or it can be both. Okay, so and this censoring can happen for many reasons. Sometimes the patients can die. Okay, so that might be one of the reasons, or sometimes it might happen this one that they left the study. Okay, so that's what it is. So this does. So the observations, so we have those censored observations. So out of this, as I said, 80 observations are censored in both variables. So that means both x and y, both variables, they are censored. So in this particular case, which means that either the patient have left the study, or it is basically that they have most probably maybe have died. Okay, so that is there. Okay, 54 and 96 observations are censored in X variables and Y variables respectively. Okay, so it is very clear. And the censored observation, I'll be denoting this one as X star. So as you can see that there are 6 observations where X is equal to Y out of these 197 observations. 3 observations where X star is equal to Y, and 37 observations where X star is equal to Y star. The reason actually I'm trying to emphasize on this one, so there is a significant amount of observations where X is equal to Y has taken place, which basically means I'm trying to emphasize that means we cannot use the absolutely continuous distribution to analyze the data set. Actually, first time the data was analyzed based on the absolutely continuous distribution, so ignoring this equality, but we feel this one that should not have been done because definitely you cannot ignore this equality observations. Okay. I hope you can hear me. Okay, is that okay?
Yeah, yes, Professor.
Okay, good. Yeah, and the second one, the second data set is slightly different, and it is again it is on the same another different experiment, but on the similar thing. But here, what we are observing basically capital T, which is a minimum time to blindness, okay, which is either can be the treated eye, the laser treated eye, or the untreated eye, or it can happen to both the eyes at the same time. Okay, so you can see this one that. So in this experiment, this is slightly different. That means that where I have the minimum time to blindness in any one of the eyes, either the laser treated eye or the untreated eye, and or it can be both the eyes. Okay, so again here also you can see that there is a positive probability that we are observing basically the minimum of X and Y, but X is equal to Y has a positive probability. Okay, so that is basically the second data set. And in this second data set, what we have observed that we have total 71 observations, and we do not have any censoring in this particular case, and we have 28 observations where delta is equal to 1, so which basically means those are the laser treated eyes. 33 observations where delta is equal to 2, and 10 observations again you can see this one that which is delta is equal to 3, that means where X is equal to Y. So you can see that out of 71 there are 10 observations where we have equality. Okay, so we simply cannot ignore these equality things. Okay, and as I had mentioned at the beginning itself, the main aim of this experiment is to study whether there is any significant effect of the laser treatment or not. So that means whether laser treatment has any effect or not. Okay, so that's what we are trying to see. Okay, before progressing further, what we have done it here, we have just provided the Kaplan-Meier estimates of the laser treated eye for the first data set. Okay, which you can see this one that which is on the top one, and the traditional one which is on the bottom one. Okay, so this is the survival function. Okay, so you can see that the survival function of the laser treated eye is lying above the traditional eye. So basically our question is whether this difference is significant or not. Okay, whether this difference is statistically significant or not. And of course we had used this one, the Kaplan-Meier, because in this particular case, because there are lots of sensory. Okay, and this is the empirical distribution function for the second data set, which are for the laser treated eye, and for the traditional I. Okay, so that's what it is. I mean, we can see this one that well, they are more or less overlapping. Okay, so yeah. So as I had mentioned that well, this one is clearly we should not use an absolutely continuous bivariate exponential distribution for analyzing data set. And so the one of the natural thing, because there is a positive probability that x can be equal to y. So natural thing what comes to our mind that the famous Marshall-Olkin bivariate exponential distribution, which was proposed by Marshall and Olkin. Okay, so let me just put it that there are to create this what we call this one the singular bivariate distributions. That means where there is a positive probability x is equal to y. There are mainly two main approaches. One is called the minimizations approach, which was proposed in this famous paper, JASA paper, by Marshall and Olkin way back in 1967, and they have used this the minimizations approach, and it's a very simple, but I think very interesting technique. And the nice part is that it has lots of this physical interpretation also. I'll come to that. And other one, what we had proposed, which is the maximization technique, which came out in the Journal of Multivariate Analysis. The idea was very similar, but of course the interpretations are totally different. So we had developed the several properties and the estimation procedures and things like that. Okay. So, but in this case, of course, we'll be looking at the minimizations approach. Okay. So this Marshall and Olkin introduced this bivariate exponential distribution, and as I said, the idea is very simple. What they have done it, they have done it basically from the three independent exponential random variables x1, x2, x3 with the parameters lambda 1, lambda 2, lambda 3, and then what they have done, they're looking at x is equal to the minimum of x1 and x3, and y is equal to the minimum of x2 and x3. Okay, so that is basically the way they had put it. Okay, so now we can see that one because of the presence of x3. Although x1, x2, x3 they are independently distributed, but x and y they are dependent. Okay, x and y they are dependent because of the presence of x3. And not only that, and because of the presence of x3, there is a positive probability that x can be equal to y, because you can see that if x3 is less than x1 and x2, then clearly x is equal to y. Okay, so probability x is equal to y is same as probability x3 is less than the minimum of x2 and x3, which simply turns out to be lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3. Okay, so that was the simple basic idea about this the minimizations one, and it has a very nice interpretation in terms of the homogeneous partial process, and that's what it is. That's what it is, and that's the reason that you can think of this one as a if you're looking at it from the physical interpretation, as if the shocks appear. Okay, and the shocks appeared following a Poisson process. So that means the inter-arrival time of the shocks are exponential distribution. And suppose the shocks of the type 1 occurred with the homogeneous Poisson process with rate lambda 1. The shocks of the type 2 happened with rate lambda 2, and the shocks of the type 3 happened rate lambda 3. And the shocks, as soon as the shock someone fails, if the shock 2 appears, the component 2 fails, and if the shock 3 appears, both the components fail. Okay, so so that's a nice interpretation what we have. So if you're looking at the component lifetime of the two components, that is an x and y. Okay, that's what it is. Okay, so it's a very nice interpretation what we have, in this particular case, you have this probability density function also, but the the interesting part about this Marshall-Olkin bivariate exponential distribution, and that's the way they had developed this. You can see this one that there are three components in the density function. One component is on the area y less than x. Another component is on the area x less than y, and another component is on the area x equal to y. So as you can see, there are three components. So there are some technical issues here. I just like to mention that, well, when you are trying to define a density function from a distribution function, so you have to have a dominating Lebesgue measure. In this particular case, it is not the usual dominating two-dimensional Lebesgue measure works because you have this peculiarity or you have this singularity on the line x is equal to y, because in any absolute continuous distribution function on x is equal to y, the probability is 0. But here, of course, you have a positive mass which has this f naught x things. Okay, so those are the things you have to take care from the technical point of view. So that means, baseline hazard of s naught x. So that's the reason this one that it is called the proportional hazard. So the hazard function of any member of the family is proportional to the hazard function of the baseline one. So that's the reason that it is called the proportional hazard. So now it is very easy to see that if S naught is a survival function, then of course S naught x to the power lambda for any lambda greater than 0 is also a survival function actually. Okay? So that can be easily shown. So we are looking at that class. So you can see this one that way. If you take S naught x is equal to e to the power minus x, that becomes an exponential. If you take e to the power minus e to the power minus x to the power alpha, which is an variable, so it's a, but S naught x can be any survival function actually. Okay, there is no need to be any specific one. Okay, so now suppose my x1, which is S naught x to the power lambda 1, x2, which is S naught x to the power lambda 2, and my x3, which is S naught x to the power lambda 3. Okay, so just like the exponential one. So you can come back to the exponential case if you take S naught x is equal to e to the power minus x. Okay, so the same way. So bivariate proportional hazard class, we'll be defining it as x is equal to the minimum of x1 and x3, and y is equal to the minimum of x2 and x3. Okay, that's the way we can define the bivariate proportional hazard class. Okay, so now, as we had said that, well, this S naught x, you can take it to be exponential, you can take it to be Weibull, you can take it to be Rayleigh and things like that. So there you are making some specific assumption on the baseline one, and that means you are making a specific assumption of the shape of the hazard function. Shape of the hazard function, you are making some specific assumption. But what we are proposing that, well, let's not use any specific parametric formulae, but rather than that, let's consider a density function of the baseline one, which has a piecewise constant hazard function. Now, what is a piecewise constant hazard function? Piecewise constant hazard function, what is in the form? Suppose we have m, what we call the m cut points. Okay, so it is being characterized by the number of cut points and the constants of the form of theta j's. Okay, so it is basically, I have the cut points tau 0, tau 1, tau n. We can take tau 0 to be 0, tau n to be infinity. So so there are n cut points, and we have those hazard constants theta 1, theta 2, theta n. Okay, so that's the way it is being characterized. So what it basically means, that means the baseline hazard function h naught t, which can be written in the form of summation theta j times that indicator function. Okay, so indicator function is 1 as long as its t's belong to this tau j minus 1 to tau j 0 otherwise. Okay? So basically that is the piecewise constant hazard function. Now, once you have this piecewise constant hazard function, so you can easily write the survival function, you can write the density functions and all these things. Okay, so that's what we have done. We have taken the hazard function to be piecewise constant. So once we have this one, I should be able to write down the corresponding the likelihood function. Okay, because I can write down the density function, I can write down the survival function all these things. Okay. So one more thing I would like to put it here. One of the major motivation of using this piecewise constant hazard function is that, say, if you use any specific parametric density function, say for example Weibull or the Rayleigh or log normal and things like that, in that case, that means you are assuming a priori that the baseline hazard function is constant or increasing or decreasing and things like that. On the other hand, if you take this piecewise constant hazard function, then you are not assuming a priori what should be the shape of the hazard function. I mean, it is basically a data-driven technique. Okay, it is a data-driven technique. The data should tell you, what kind of hazard function, what kind of shape of the hazard function it should take. Okay, so that is basically, yes.
Yeah, 5 minutes more.
Yeah, sure. Yeah. So that is basically the whole idea about this data-driven hazard function, and that's what we have. Okay, that is basically the whole idea. Okay, so now let's look at the priors and the posterior. So basically, you can see that now we have what are the parameters? The parameters are lambda1, lambda2, lambda3, which are coming from those s naught x to the power lambda1 from the x1, x2, x3, and we have from the baseline we have this parameter theta1, theta2, theta. Okay, for the time being, we are assuming it the cut points are known, but later on, of course, we have estimated those things, and I'll tell you how. Okay, so we are assuming that the tau y's are known, and that's the way it has been there. We have assumed a very, very flexible prior on the lambda1, lambda2, lambda3, and this particular prior is known as the Dirichlet gamma prior, which the reason actually it is very, very popular one, because it's a very flexible one. The independence comes out as a special case. It can be positively correlated, negatively correlated, depending on the hyperparameters and things like that. Okay, and it was first proposed by Pena and Gupta in JRSSB in case of the Marshall-Olkin bivariate exponential one. So we have taken the same prior, and we have assuming this on this theta1, theta2, theta m has a Dirichlet prior. Okay, and they are independently distributed. Okay, so we can write down the posterior in this form. So the nice part about that one, that we have a product of the 3 gamma. Then in case of the first case, that means where I have the bivariate data for the data set 1, and then I have a Dirichlet prior, Dirichlet posterior, Dirichlet distribution, and then I have some importance function h of lambda. And the same thing over case 2, we have this Dirichlet gamma prior, then the Dirichlet gamma posterior, Dirichlet gamma density function, the Dirichlet density function, and h of lambda. These two h of lambda are different. I mean, they're not same. Okay. We have proposed a very convenient procedure to generate sample from the Dirichlet gamma. So that those things can be done very easily, and that's what it is. And now, because of this particular structure, very convenient important sampling technique can be used to estimate, to get the estimates of the parameters, and to get the credible interval also. Okay, so those things are quite possible. Okay, so we have done the data analysis. In the first case, we had put the best model, because here actually what we have used this estimation of the tau i's based on the, in this particular paper we have not done it using the non-homogeneous Poisson process technique, but recently we have developed that method, and it is working very well. So in this particular case, what we have seen, this one, that m is equal to 3 and tau 1 is equal to 0.5, tau 2 is equal to 1, works the best among different model. And this best model we have obtained it based on this AIC-BIC criteria, and these are the parameter estimates what we have got. And I had mentioned about the testing of hypothesis, lambda 1 is equal to lambda 2, and lambda 1 is equal to lambda 2 basically gives you that the two treatments are equal, and the base factor turns out to be very, very low, which basically means that we reject the null hypothesis. hypothesis. Okay, that means there is a significant effect of the laser treatment, and that's what we have observed in the data set 1. Okay, for the data set 2, we have observed that m is equal to 2 provides the best fit, tau 1 is equal to 0.98, and those are the estimates. And in this particular case, when we have this lambda 1, when we are trying to test lambda 1 is equal to lambda 2, in this particular case, the base factor turns out to be 4.6088. And and according to the Bayesian literature, since it is considered to be high, we cannot reject that. So in that second data set, we cannot say this one that laser treatment has any effect, whereas in the first data set, that's what we have observed. Okay, and that's it. And thank you for your attention. Thank you very much. Yeah.
Thank you very much, Professor Debashish Kundu. Now, any open for the questions, queries from the audience?
Hello.
Hello. Yes.
I am Professor Ilangon Gundu.
Yes. How are you?
How are you? Fine, Gundu.
Okay. Yeah. Tell me.
Yeah. Is it any data set available for the analysis to be done for your work?
Yeah. These are openly accessible.
Oh,
these are openly, these are openly accessible. Actually, we had put the data in the paper also, so you can.
Fine.
Yeah.
Just tell you. Yeah. Thank you very much, Gundu. I really enjoy your lecture. Very. It is useful for our scholars also. Thank you very much, Gundu. Thank you.
Yeah. Sure.
Any other questions? Any other questions? Debashish, I have one query.
Yes.
Not a question actually. Maybe in the slide number 7. Okay.
What is that? What is that?
In the slide 7.
Oh, it's a 7. Okay, just 1 minute. Let me just go back.
It is not actually question. 7. Next one.
Oops. What happened?
Next slide. Yeah. Just maybe it may be a typo error. I don't know. 187 observations are there. If you add all this, it comes out to be 196.
Oh, is that? Oh, okay.
Yeah. I don't know whether it is somewhere it is some number.
I have to check that one. Okay, good observations. Yeah, I have to check that one. Yeah, that might be. I'll just check that one. Sure. Okay, good. Thank you. Yeah. Very nice. Okay.
If there are no other questions, let us thank the speaker for a wonderful and innovative talk.
Okay. Thank you. Yeah. Okay, so I'll stop sharing.
Yeah, you can stop sharing. I introduce the next speaker, Professor Somesh Kumar from IIT Kharagpur. I am just giving the brief introduction. Professor Somesh Kumar has a research interest in the area of statistical decision theory, inference. He has published more than 130 research papers in reputed international journals and books chapters. In particular, he has made theoretical contribution to problems of estimation, where when the parameter space is restricted by prior considerations. He has a lot of important topics. I'm just giving some few of them. He has supervised more than 14 doctoral students, and he has published more than 250 masters dissertations. He as an associate editor, editorial board member, and viewer of many national and international journals. He also received Professor K.S. Rao Best Research Award from Indian Society for Probability and Statistics in 2022. He has been elected member of International Statistical Institute, Netherlands in 2022. He has also video courses on probability and statistics, statistical inference, statistical methods for scientists and engineers. They are available in the website. NPTEL, and YouTube.
Hello.
He visited several universities, several universities at abroad, namely University of Ulm, University of Dortmund, in Germany, and Middle East Technical University, Ankara, University of Wollongong, Australia, University of Salzburg, Austria, University of Colombo, Sri Lanka, and several other places. Uh, I know him very well from last. We used to meet him in almost all conferences, mostly in the ISPS, and here also with the Satish Kumar conferences. And over to Professor Somesh Kumar.
Uh, Thank you very much, Professor Hanagal, actually, for giving a lot of introduction. And I thank Professor Satish Kumar. And it is due to him that actually we are able to meet all the prominent statisticians actually quite often, at least 3-4 times in a year. Actually, 2 times he is conducting, then ISPS is at least 2 times in a year. So we are able to meet, and it's a very good way. Even sometimes we are not physically traveling, but we are just meeting, so it's good. So now let me share my screen and just please tell whether it is visible. Mm. So is it visible now?
Yeah,
Yeah,
yeah.
visible. Yes, it is visible.
So the topic of my talk is new test for simultaneous ordering in a two-way additive ANOVA model. So this is actually the work of my research scholar, Mr. Raju Dey. So we have actually published one paper already in Biomedical Journal. And so for the same problem, we have proposed some now new tests. So and these turn out to be more powerful than that. And this is under now.
Sorry പറഞ്ഞാലേ എനിക്ക്
We are
തോന്നുന്നു
submitting this paper.
പഴയതാ എടുത്തിട്ട് നെറ്റിൽ കറക്റ്റ് ഇട്ടിട്ടുണ്ട്. ഞാൻ വിളിച്ചു പറയണം. ഇത് വിളിച്ചിട്ട് നീക്കിലാണെന്ന്
I'll just, I think, remove this one and then I'll again reshare. I think there is some problem with the buttons. I'll just check it. Yeah.
വിളിച്ചു പറഞ്ഞു.
Yeah, the slides are not moving. I don't know what happened.
Maybe you can check. You can go to the direct slide in your laptop, not in this one. There you can move, whether it is moving or there. In your laptop, this file is moving.
കോൺഫറൻസ് വെബ്സൈറ്റ് ചെയ്തിട്ടില്ലേ അതില് സാറിന്റെ പേര് ക്ലിക്ക് ചെയ്യുമ്പോൾ CV വരുന്ന രീതിയിലാണ് വെബ്സൈറ്റ്. പക്ഷെ അനൗൺസ് ചെയ്യുന്നത് ഹലോ എന്തോ സ്ട്രെങ്കി ഞാൻ ഇന്നലെ മെയിൽ ചെയ്തിരുന്നു. കിട്ടിയോ? കിട്ടിയെങ്കിൽ പറയണേ. സ്റ്റാർട്ട് ചെയ്യുമ്പോ കട്ട് ചെയ്യണ്ട. അപ്പൊ സ്റ്റാർട്ട് ചെയ്യാൻ നേരത്തെ ഒന്ന് പറയണേ.
Equality of treatment effects against the alternative of at least one inequality.
Hello? Stringy. അസിസ്റ്റന്റ് ഗ്രൂപ്പത്തോടെ ഞാൻ അയക്കുക. ഇത്തവണ വന്നിട്ടില്ല. ഇത് പഴയത്. റിട്ടയർ തന്നിട്ടില്ല. അങ്ങനെ അസിസ്റ്റന്റ് ഗ്രൂപ്പിലേക്ക് വാട്സാപ്പിൽ ഇത്
independently distributed with common mean 0, but it is not identical. So variances are heteroscedastic. We are considering the ijth cell variance as the sigma ij square. So you can think that this problem is in the most generality. That means so some of the data sets actually, when we looked at the box plots, then we observed that these data sets are actually showing increasing responses for both the sides. So because of that, this problem we have thought about, because one-sided or one level increasing work we have already seen, and we have also made some contribution to that. So for example, if you look at the study of anemia, so this is a serious global public health problem, and it is usually diagnosed according to the lower limits of the hemoglobin, which is proposed by WHO in 1968. And now many demographic factors, for example, gender, age, altitude of the residents, etc., they influence the levels of hemoglobin and the prevalence of anemia. So there are a lot of examples and data sets given in the Garcia et al. So if we consider two factors here, so two-way layout model by taking HB levels as the response variable and the age groups of elderly populations as factor A and the residence altitude as factor B, then we expect that the HB levels increase with the age group and decrease as well as with the usual as the I think I made a mistake here. As the age group increases, then the HB levels decrease, and if the altitude increases, then also the hemoglobin levels increase. So here if we consider factor A as the age groups and the factor B as the resident altitude, then we have this monotonic increasing things here. Similarly, there is another study on the what we call RSPM values, respirable suspended particulate matter, and if we consider the years as well as the cities, then it is observed that as the density of the population increases, then RSPM values increases. Problem, but it is against the ordered alternatives. So Sharrock in 1967, he has considered the test imbalanced and homogeneous two-way additive ANOVA. And Williams in 1971, he proposed a trend test statistic for testing the mean response of normally distributed populations against trends based on the difference between the MLEs of the largest and the smallest mean responses. Then Kulatunga and Sashabuchi, they have considered the likelihood ratio test for testing homogeneity of both row and column effects against simultaneous ordered alternatives in a two-way additive ANOVA model when the sample size is 1 in each of the cell and variances are equal but known. So the problem that we have considered, a much, you can say, elementary version of that has already been studied in 1984, way back almost 40 years back. But as you can see that they considered the very simple model that the variances equal and known, and also the sample size, that means they have taken only one replication in each cell. Then Hayter in 1990 developed simultaneous one-sided confidence intervals for all of the ordered pairwise differences of the treatment means in a one-way ANOVA with homogeneous error variances and extended it for certain contrasts of the ordered treatment means. Then Miwa and Hayter in 1999, they have considered simultaneous two-sided confidence intervals of the differences of all treatment effects when the average treatment effects are all far apart. Then Moonsinghe and Wright in 1995, they have considered H0 that mu ij is constant against the alternative H1 mu 1 j less than or equal to mu I prime j prime. Response studies. Then recently, Mandal et al. In 2023, they have developed the test procedures for testing homogeneity of main effects against their ordered alternatives in two-way additive ANOVA when the cell frequencies are unequal and error variances are heterogeneous. So here you can think of this is the preliminary version of our work. Here one, that means ordering among alpha I's or beta J's has been considered, not both. Now here you can see that we are considering simultaneous ordering. So we consider H0 that all alpha I's and all beta J's are equal, and we consider the simultaneous ordered alternatives alpha 1 less than or equal to alpha 2 less than or equal to alpha A, beta 1 less than or equal to beta 2 less than or equal to beta B. So as you can, as I'm just mentioning, the preliminary versions of this problem are that we can consider only alpha I's or only beta J's in additive or even the crossed two-way model. That problem has been studied even in the heterogeneous and unbalanced sample sizes model. But the simultaneous ordering problem has not been considered. So one problem that we considered, that if we consider LDL, that means the low density lipoprotein, so we consider the clinical profiles of number of patients. So here LDL is the bad cholesterol, which causes plaque built-up in the arteries, increasing the risk of heart diseases and stroke. High LDL levels are risk factor for diabetes also. So to study the effect of age and gender on LDL, we can model the problem as a two-way ANOVA model by considering LDL as the response and age as a factor A and gender as the factor B. Since most women experience menopause between the ages of 45 and 55 as a natural part of biological aging, the ordering of the effects of the levels of factor gender on LDL get reversed after the age near 50. So we have considered the following two different two-way ANOVA models. In the first model, we are considering LDL as the response variable, factor A as age, having three levels: age between 20 to 29, between 30 to 39, between 40 to 49, and factor B as the gender, having two levels, female and male. So if you look at the box plots of the population data sets here, in this figure 1 you can see. So for females, if you see, this box plot shows 30 to 39 and the green one denotes 40 to 49. Similarly, if we consider male population, you can see this median part is increasing here. At the same time, if we compare between females of 20 to 29 and males between bar here. Similarly, if you see between the age group 30 to 39, the MLEs of the parameters under omega naught and omega numerically. Gauss-Seidel type of nonlinear solution method, we have to choose some initial approximation or initial solution here for mu and omega. So two algorithms are required because in the likelihood ratio method, we need the maximum likelihood estimators under the null hypothesis space as well as the full parameter space, which we are denoting by omega naught and omega respectively. This type of algorithm we have proposed, and then of course we have actually proved the existence of the solutions. Uniqueness of course is true only under certain conditions, but then what we are getting, because we are obtaining algorithmic solutions, so what we are doing is that if there are more than one solution, then we are checking the value of the likelihood function at all those values and then choosing the one which actually gives the maximization. And then the convergence of the algorithms to the true value has also been established. So those results I am not presenting here. Now based on this, the likelihood ratio statistic is given by the equation number 4.8. We call it W1. So so the W1 will reject the H0 at the level of significance alpha if W1 is less than C, where C is the critical point. That means the probability, or you can say the size of the test must be equal to alpha. Now, as you can see, the methodology of the solution as well as the expressions, because these are all obtained algorithmically. So we don't have any analytic representation of W1, etc. So, and another thing is that one can suggest that we can use asymptotic version of that is asymptotic chi-square test. But to derive the asymptotic chi-square test, also we have certain regularity conditions, and when we have the full parameter space of this nature, where orderings are placed on the parameters, etc., then we are not able to satisfy those conditions. So therefore, the asymptotic chi-square distribution is also not valid here. So what we do, we propose a parametric bootstrap approach here. So we generate the bootstrap samples xij star from normal 0 Sij square, and then based on that we calculate the bootstrap version of the likelihood ratio statistic called W1 star, and we consider so we for each iteration we generate say 10,000 times these bootstrap values and calculate this W1 star every time, and this we order these W1 star values and take the alphath quantile. So this is the bootstrap critical point C star, which we consider as an approximation to this value C. Therefore, the question arises that how good is this approximation? Will it be all right? So we need to prove the asymptotic accuracy or the validity of the parametric bootstrap here. Fortunately, we are able to prove this using the Kullback-Leibler divergence measure. So we are able to show that the conditional distribution function of the bootstrap likelihood ratio statistic W1 star given the original sample and the null distribution of the likelihood ratio statistic, they are almost the same. So basically we establish it using Kullback-Leibler divergence measure, and then of course it's not just a one-way thing, like we have to actually prove several theorems in between, but ultimately the result is proved. Yeah. So this shows the validity of the parametric bootstrap procedure for this kind of problem here. Next, one problem with the likelihood ratio statistic is that firstly we need algorithms for finding out the likelihood ratio test, and then secondly the parametric bootstrap, which becomes so computationally this is somewhat you can say challenging and computationally complex problem. So we have actually developed a R package here, and we have actually hosted it on the open source GitHub there. So anybody who has a data set, he can actually directly use it. So earlier we used to have statistical tables in the books, but now we have the packages and one can just use it. So it has been incorporated in R. So we thought to reduce the computational complexity, we can consider the test based on the pairwise differences of the consecutive means. So now since it is a two-way model, we will have consecutive means in two directions. One is in the direction of the factor A, which we denote by T1i. So this is xi plus 1 dot bar minus xi dot bar divided by I square root 1 by b square, and then this sample variances divided by the corresponding sample sizes. So this is basically, you can think of Welch-Smith Satterwhite type of test function here, which we generally use x bar by minus y bar kind of thing. So it is actually the version of that. And similarly, in the direction of the factor B, we consider T2j, which is x dot j plus 1 bar minus x dot j bar divided by similar kind of variances here. So T1i for I is equal to 1 to a minus 1, and T2j for j is equal to 1 to b minus 1. Now, based on this, let us consider the vector of the simultaneous differences. T1 is equal to T11, T12, T1a minus 1, and T2 is equal to T21, T2 b minus 1, etc. So we look at maximum of T1 and maximum of T2. And now again we take a maximum of that, which is called W2. So this is another test statistic which we are able to define here. Okay. So if we reject using this one, W2 is greater than SC2, where C2 is the critical point here, then it means that there is at least one inequality among alpha i's or beta j's. So this is again testing the same hypothesis with which we tested the likelihood ratio test statistics. So they are testing the same thing. Only thing is that this is much simpler because it will use only one level of algorithm, because calculation of this T1, T2, etc. is quite simple. So this is straightforward because given the data, you can just calculate. So it is reducing the computational complexity. So naturally, the question arises: how much is the loss in the power? So that study we have done. So once again, the parametric bootstrap procedure is given for that same thing, and we have this bootstrap statistic W2 star, and then we can actually look at that. Another version, or you can say another variation also we have proposed. In place of the max T1 and max T2, we are considering min T1 and min T2, and then max of this. It means if we reject using W3, it means that there is at least one strict inequality throughout, either in alpha i's or in beta j's. So sometimes this kind of hypothesis is also important. So as a curiosity, we have actually analyzed this one also, and we actually find that this test also gives quite good results actually. So these three statistics we are having, one based on the likelihood ratio, and W2 and W3, they are based on the pairwise, consecutive pairwise differences among the alpha levels and beta levels, A levels and B levels. So once again, using the Kullback-Leibler divergence measure. In fact, one can use Hellinger distance, etc. also, that we have done, but here we have considered only one type of proofs. So this again shows that the bootstrap procedure for implementation of test statistics W2 and W3, they are also asymptotically accurate. So this is proved in theorem 2. We are also able to derive simultaneous one-sided confidence intervals. So if we reject the null hypothesis of equality, then we may be interested to check the pairwise differences between alpha 1, alpha 2, alpha 2, alpha 3, similarly between beta 1, beta 2, beta 2, beta 3, beta 3, beta 4, and so on. Okay, so we can use this statistic W2 for creating the simultaneous confidence intervals. So if we consider, say, C1i denotes the contrast alpha I plus 1 minus alpha I, C2j denotes beta j plus 1 minus beta j. So we look at this T1 tilde I. So where we have adjusted this xi plus 1 dot bar minus xi dot bar by their respective mean effects of mean row effects or the mean column effects here in T2 1 tilde I and T2 tilde j bar. So we consider this, and we look at this W2 tilde as the max of T1 I tilde, max of T2 j tilde. Then if we consider probability of W2 tilde less than tau is equal to 1 minus alpha, then this leads to 101 minus alpha % confidence intervals, simultaneous one-sided confidence intervals for C1i as well as C2j. This is the pair-wise consecutive differences. And these turns out to be in this particular form, equation number 4.16 and 4.17 here. So this value of tau needs to be determined. So to determine this, again, we have to use a parametric bootstrap approach here, because from here, this value in analytic form we cannot calculate. So then we have done extensive simulation studies for our test procedures as well as the confidence intervals. That means whether the procedures achieve pre-assigned type 1 error and they have a good power performance. We have done the calculations for nominal type 1 error as 0.05. In order to see whether the proposed test control the nominal size, we have considered various kind of parametric configurations, as well as different type of sample sizes. So we have considered various cases like balanced two-way designs, moderate and highly unbalanced two-way designs, homoscedastic two-way designs, moderate and highly heteroscedastic two-way designs, etc. So all type of cases have been considered just to check whether our test procedures actually work well in all the cases. Fortunately, it turns out that here we have presented few results. So, for example, for A is equal to 3, B is equal to 3, that is a 3 by 3 design. We have considered sample sizes. As you can see, N21 shows equal and small sample sizes. Then you have unequal and moderate sample sizes. Then you have unequal and slightly large sample sizes, and so on. So all kind of sample sizes, all kind of variance combinations have been considered. As you can see, sigma 21 square, sigma 22 square, sigma 23 square, and so on. So all these things have been considered. Now, if you look at the tabulated values of the empirical size values, you can look at this W1, W2, W3, W for all these combinations. You can see that W1 is closest to 0.05, but W2 and W3 are also not bad. Actually, they are also very, very close to 0.05. So, in fact, we can say that all the tests achieve the nominal type 1 error rate satisfactorily for all the configurations. So they control the nominal size even when the error variances are positively correlated with the sample sizes or negatively correlated with the sample sizes. And we have considered 3, 2, 3, 3, 3, 4, various kind of levels. In fact, we have done for larger also, but that we have not presented here. So for power curves, we have actually considered increasing differences between alpha i's and beta j's. So if we fix some alpha and beta, and then we consider xi alpha and xi beta, then we increase xi.
Sumesh, you have 5 minutes more.
Okay, so yeah, I'll try to complete it within 5 minutes. Yeah. So if we increase the value of xi, that means we are going more and more into the alternative hypothesis parameter in space. So that should show the increasing power values. So fortunately, it turns out that it is the case here. So we have considered 4 distinct scenarios based on the sample sizes and cell variances. Small sample, moderate heterogeneity; small sample, high heterogeneity; large sample and moderate heterogeneity; large sample and high heterogeneity. And you can see here, in all the cases, this W1, that is the likelihood statistic, it has the higher power values as compared to the test based on the pairwise differences. Among the pairwise differences, you can see that there are cases where W1, W2 is better, and some place where W3 is better. But in all the cases, the likelihood statistic actually performs far better. So as you can see that this is a compromise. That means the solution given by pairwise differences, it is useful to reduce the computational time, but at the same time there is a compromise on the power values. That means sometimes the test based on pairwise differences may not reject, but LRT will still reject. So that can detect even the smallest of the differences between the factor levels. As you can see, this large sample, moderate heterogeneous, large sample, highly heterogeneous. In all the cases, the likelihood ratio test performs better, and there is a trade-off between W2 and W3. For the smaller differences, W3 performs better. For higher differences, W2 performs better. Okay, so I have already mentioned this, that the power values of the test statistic W1 are the better than all of the things. We also went through a robustness studies. That means if there is a deviation from the normality, so we considered non-normal symmetric distributions, that is contaminated normal, Laplace, T distribution, uniform distribution, and we also considered some skewed distributions like mixture of two normal, chi-square, exponential, Weibull, log normal, etc. And we went through again the same exercise of conducting the size and power comparisons, and the conclusions are that W2 and W3, they control the type 1 error rate for all the distributions except exponential and log normal, whereas the likelihood ratio statistic achieves the type 1 error only for symmetric distributions. So that means the likelihood ratio test, which was the most powerful among the three tests, from the robustness point of view, it is not that good. It is good for the symmetric cases, but for the non-symmetric cases, W2 and W3 still perform better. Then, as I mentioned, that we implemented it on the data set on the LDL values. We have done all the preliminary things like QQ plots and other kind of things, so that this model is actually applicable. And here we are observing that the test statistics, they actually reject in all the cases. We also went for the simultaneous confidence intervals. It turns out that the simultaneous confidence intervals between the male and female, they are actually significant, but for alpha values, they are not significant. So these are the values that we get, because this alpha 2 minus alpha 1 and alpha 3 minus alpha 2, they include 0, but this one does not include the 0 here. So maybe I think I can stop here. This is the previous version of this work, where which we have published in Biometrical Journal, but we could not develop the likelihood ratio test at that point of time. So we have given the test based on the simultaneous differences and some preliminary version of, you can say, likelihood ratio. But here we have been able to develop the full-fledged. So now we will be submitting this paper somewhere. Thank you.
Okay. Thank you, Professor Somesh Kumar. Now it's open for the questions, queries from the audience. Any questions, queries?
Good morning, Professor Somesh. This is Narendra this side.
Yes, please. Yeah.
So it was a very interesting presentation. So though I joined a little late in between, but I have a very elementary question, I would say. So in between, you had two statistics, which was labeled as W's and all that.
W2 and W3, yeah.
One was based on max of T1
yes,
and max of T2, right? And there was another one.
That is based on min.
Yeah, min. So I've not understood the second.
Yeah. So if the min statistic rejects, but here it is, of course, a combination. Actually, we started with this min-max when we were considering one-way ANOVA model. That work has been published in statistical papers. So there, what happens is that if you reject with the max, it means at least one strict inequality. Whereas if you reject by min, it means all of them are strictly, that means all strict inequality. That means alpha 1 less than alpha 2 less than alpha 3, etc. Now, in the context of this two-way simultaneous model, what does it mean? Here it is slightly complicated because max with the T1, it rejects means that alphas have at least one strict inequality, and similarly for T2, that at least one beta j's has a strict inequality. And then with max of that, we reject. That means at least one is strict inequality and at least one alphas are beta j's. Whereas with W3, it is max of min. That means at least one complete strict inequality either in alphas or beta j's. So what we observed, since in the example that we have done, we actually rejected using both W1 and W2. Then we went for the confidence intervals, and it turns out that actually there is a strict inequality in beta, but not in the alpha. So which is confirming to this one. That means since it was rejected using W3 also, that means we suspected that, and actually it turned out when we looked at the pairwise differences.
And in both cases, the nominal level is attained.
Nominal level is attained for all the three test procedures. Yes, W1, W2, W3, all of them are very close to 0.05. Yeah.
Right. Thank you so much.
Okay. If there are no more questions,
I think Dr. Raghavendra Sharma has some question.
Okay. All right. Okay.
Dr. Sharma?
Dr. Sharma, do you have any questions?
Professor Anagal, chair.
Yeah, please.
Yeah, Professor Longovan.
Yeah.
Good morning. One small question. For your application, is there any real data set used? You can use the secondary data for this.
Yeah,
purpose?
this is actually a real data set. This is basically some hospital data set that we got basically. It is based on the heart disease data actually. It is taken from NHS actually. And it is available in the public domain. And what we have done, because the data sets are huge, so it is something like population. So what we have done random sampling from there for each of the cells, and then we have. So it's a real data. It's not a artificial data here.
For the collected data set, your model give consistent result.
Yes.
Is it a robust one?
It is robust also. Yes.
Thank you for your nice presentation. Thank you very much. Professor Anagal, thank you.
Any other questions?
Yeah.
Okay. If there are no questions, let us thank the speaker, Professor Sumesh Kumar, for a wonderful talk, innovative talk. I think now over to Satish Kumar.
We have two wonderful talks by one Professor Kundu and Professor Somesh Kumar. Very informative and useful for the researchers, those who are interested in the area. I'm very much thankful to you, professors, for your support to WSTA 2024 through your deliberations. Thank you so much, Professor Somesh Kumar and Professor Kundu. Also, we would like to extend our gratitude to Professor Hanagal for your support to us through chairing the session in a very nice way and concluded in time. Thank you so much, Professor. Thanks a lot. Now, 10:28. So we have a 10:30 next session will begin. I hope Professor K.S. Banu is here to chair.
Morning to everyone, sir.
Good morning, Professor.
Yeah.
Well, just a minute. Sobna is here in the group. Sobna, please introduce the chair and do the needful and support her for the smooth running of the session. Thank you.
Okay, sir. Good morning, good afternoon, and good evening to all. We are moving on to the 7th technical session of WSTA 2024, which is a special invited session that shall be chaired by Professor K.S. Banu, retired head to the Department of Statistics, Institute of Science, Nagpur. Now, Dr. K.S. Banu is professor at Atlas Skill Tech University, Mumbai. She has more than 4 decades of teaching experience.
Very happy to be associated with this event year after year, and I'm very happy to chair this session today. Good morning to everyone. We have two speakers today. One is Dr. Sangeeta Chopra, and the other is Professor P.K. Das. Dr. Sangeeta, madam, are you here? Dr. Sangeeta Chopra, ma'am.
Yes, ma'am, I'm here.
Yeah, good morning, ma'am.
Good morning, good morning. So mine is first or?
Yours is first, ma'am.
First, okay. So there is some change because I was thinking that it is at 11.
Okay, should we then, should I ask Professor Das first?
No, it's
whatever
okay.
is convenient.
I'm ready, ma'am. I'm ready.
Okay, ma'am. Welcome to this session. I take pleasure. I'll introduce you to all of you, ma'am. Professor Sangeeta Gupta.
Sangeeta Chopra.
Sorry, I'm really sorry.
Dr. Sangeeta Chopra.
Yeah, that is why I got a bit confused. Professor Sangeeta Chopra is professor at the Department of Statistics, Punjab University, Chandigarh, since 2006. Her academic qualifications include MSc, MPhil, PhD in statistics from Punjab University, Chandigarh. Besides this, she has also done her MA in English from Punjab University. She has a vast teaching experience of 40 years and her research experience and has a research experience of 38 years. And her research areas include applied statistics, income inequality and Lorentz dominance, statistical inference and Bayesian statistics, statistical quality control, environmental statistics, etc. She has guided 9 students for their PhD and one student is currently pursuing his PhD under her guidance. Besides this, her MPhil dissertations, she has supervised 10 MPhil dissertations and 4 research projects. She has been appointed examiner for MPhil and PhD at many universities and conducted Viva examination. She has been appointed as an external supervisor in the University of Malaysia in the Faculty of Computer Science and Information System by the Dean School of Graduate Studies, University Technology in Malaysia. She has authored books on Bayesian estimation and related inference per Pareto distribution, which was published in 2018. She has a very good academic background, and she has received the 8th Venus International Women's Award for Lifetime Achievement in Statistics in Science Discipline in March 2023. She is a life member of various professional bodies like ISPS and Indian Society for Medical Statistics. Besides this, she is the executive member of ISPS. She was the executive member of ISPS for the period 2014-15, 15-16. UGC nominee for UGC SAP in 2016-21 in the Department of Statistics and Operations Research, Aligarh Muslim University. She was nominated as the member of Postgraduate and Undergraduate Board of Studies for Khalsa College, Patiala. She has been appointed as member of Board of Studies of the Department of Statistics in the Central University of Mahendragarh, Haryana for 3 years with effect from 2022. She has also been appointed as member of Board of Studies in Statistics in the Punjab University in 2021. She has participated in various conferences, more than 50 international and national conferences, and delivered talks as resource person and had chaired various technical sessions as well. She has also was the co-chair of the 19th International Conference of Forum for Interdisciplinary Mathematics held at the Department of Statistics, Punjab University. She has also been instrumental in organizing many national conferences and workshops in the department. She has published more than 50 research papers in various leading national and international journals and has been a member of the reviewing committee for some important international journals like Communications and Statistics, Simulation and Computation, MASA, etc. Madam also has a vast administrative experience, having worked twice as chairperson, Department of Statistics, Punjab University, member of the UGC Expert Committee in Statistics from 2012 to 17, member of the Advisory Committee of UGC, has been a member of various selection and screening committees in Punjab universities as well as other universities, has been the placement coordinator of the departmental placement cell since 2005 till 11, and has also held the important post of coordinator for the IQAC cell of the department for the session 21-22. With this enriching background, it's a pleasure, madam, to invite you here to deliver your lecture. May I please invite you? You have roughly 30 minutes for the lecture, plus 5 minutes for question-answer session. Over to you, Sangeeta ma'am.
Thank you. Thank you, Professor Bhanu, for the nice introduction. First of all, I would like to thank Professor Satish Kumar for giving me the invitation to interact with all of you on this academic platform. So I think last couple of years I am associated with this international webinar. So this year also I am there. So I hope we all will just get the benefit of our interaction. So I'm just going to talk on, I will just start with this. So I will be talking on some Lorentz ordering in case of power distribution. Let me first.
Okay, is it Professor Kanchan Jain?
Yeah, hello?
Yeah, is it Kanchan Jain?
Kanchan.
I'm Professor Elangon speaking.
I'm Dr. Sangeeta Arora.
Oh, fine. Thank you, Mari. Go ahead. I'm Professor Elangon. Okay, fine.
Okay. I hope this is visible to you all.
Yes, ma'am. It's visible here. I hope it's visible to everyone.
Yeah, it's fine. It's fine.
Now I can start.
Yes.
My topic will be some results on the Lorentz curve and related orderings in case of power function distribution. So this is going to be the outline of the talk. Just 1 minute. Give me some problem. Yeah. So I will be just taking this sequence. First, I will be giving some brief introduction regarding the income inequality and inequality curves. Then I will come specifically to the power function distribution. Then some necessary and sufficient conditions for the dominance of inequality curves and their interrelationship in case of power function distribution. And then I will be talking about some movements of the Lorentz curve for the power function distribution and some welfare interpretations. Something has happened. Just give me 1 minute. This is not working. My laptop has got some problem. Just give me 2 minutes. I will set it. What is it? This one. It's hanging.
It's not moving.
Yeah. Now it has started working.
Yeah, it is started.
Some problem had occurred.
Yeah, no problem.
So, inequality. What is the meaning of inequality? Everyone knows it suggests a variation from some idea of equality. So, income inequality is a state of economy in which the shares of total income received by the people of that area is highly unequal. If any person receives less than his impartial share of cumulative income, the distribution will be unequal. And once we talk of the income inequality, we talk about the two stages. One is perfect equality, another is perfect inequality. So perfect equality means that all income units receive equal income, whereas perfect inequality arises when a single unit receives the entire income. So taking up this scenario, we just look at the concept of inequality. So income inequality. So naturally, this excessive inequality affects people's quality of life. It threatens the country's political stability because more people are dissatisfied with their economic status. And once we have just looked at this scenario, then till date, Lorentz curve and the associated Gini index, they remain the most popular and the important tools for the measurement of income inequality. So, because I will be talking in particular what is their role in the context of income power function and how we can just talk about the characteristics of the power function in terms of these Lorentz curves and the related curves. So, let me briefly discuss about the power function distribution. This power function distribution is a flexible model often used for the analysis of income distribution data, lifetime data, modeling of failure processes. For example, one use of the distribution is in the reliability assessment of electrical components and semiconductor devices. One strength of the power function distribution is its mathematical simplicity compared to more complex distributions like the Weber distribution. And this is a PDF, the power function distribution. It is given by the fx, which is being given. It has got two parameters. One is B is the scale parameter, C is the shape parameter. And you can just see the range also, and its mean is taken to be C upon C plus 1 into B, which depends both on the shape and the scale parameter. And when B is 1, the above density becomes this particular case, where C is the shape parameter, depends only on the shape parameter, which is termed as power function 1 distribution. And the reference is given by Georgi and all. And the parameters of these power function distributions, they have been evaluated in this scale parameter is B, shape parameter, its support is on this 0 and B, and its mean is given this much, and variance is obtained as such. And this is the graph of the power function distribution. You can just see whenever C is 0, this is in the red dots, otherwise the shape is quite different. And the power function distribution is often, as I call it, in electrical component reliability. Many statistical distributions have been used to assessment of semiconductor device and product reliability since long, but exponential distribution generally is being used. And power function distribution can be considered as a simpler substitute, may exhibit a better fit for the failure data, and provide more appropriate information about reliability and hazard rate in some situations. And so that is why sometimes it is preferred. Another advantage of this distribution is its hazard rate as opposed to the exponential distribution is non-constant and may therefore be more useful. And coming to the setup of the income distribution and income inequality, Georgie has given the Lawrence curve, Gini index, and Bonferroni index for the power function distribution and explained their use in the field of income, wealth, assurance, and reliability. And Dallas have enlightened that if X follows power function distribution, then X inverse follows the Pareto distribution. Pareto distribution is another important distribution in the setup of the income distribution. And Matatu has shown that the power function distribution is the only distribution with the property that the Lawrence curve of the distribution truncated on the right is independent of the point of truncation. So it means in the context of income inequality, it is being used. And in the context of income inequality, Lawrence dominance and related influence have been discussed by various authors to highlight various aspects of inequality and welfare industry. And Lawrence is of course important, but some other variants of the Lawrence curve is a generalized Lawrence curve, Bonferroni curve, and comic curve are also used to study different features of inequality. And it is shown that the various orderings shown by these different curves of inequality are different from the Lawrence.
ചെയ്തുള്ള പരാതി പാടൻ സ്റ്റേഷനിലെ സെക്രട്ടറി സന്ദീപിന് അവധി നിഷേധിക്കുകയും അധിക്ഷേപിക്കുകയും ചെയ്തു എന്നാണ് പരാതി വന്നിരിക്കുന്നത്. 10 ദിവസത്തെ അവധിയാണ് ചോദിക്കുന്നത്. സന്ദീപിന്റെ ബൈക്കിന്റെ താക്കോൽ ഈ CI കിരൺ സാം ഊരിയെടുത്തു. നമുക്ക് ആ ദൃശ്യങ്ങളിലേക്ക് കാണുന്നു. സമർപ്പിക്കാൻ പാലക്കാട് SP നിർദ്ദേശം നൽകിയിട്ടുണ്ട്. പ്രിയ ലോഡിമണ്ഡലം ചേരുന്നുണ്ട് വിവരങ്ങളുമായി. പ്രിയ, 10 ദിവസത്തെ അവധി ചോദിച്ചതിനാണോ അധ്യക്ഷൻ?
നാല് ദിവസം മുമ്പാണ് ഈ സംഭവം ഉണ്ടായത്. പാടകേരി പോലീസ് സ്റ്റേഷനിലെ CPO ആണ്, വടക്കഞ്ചേരി സ്വദേശിയാണ്. വന്യജീവി ആക്രമണങ്ങൾ കൂടിയ ഒരു പ്രദേശത്തെയാണ് പാടകേരി പ്രദേശം. അതുകൊണ്ട് തന്നെ കഴിഞ്ഞ കുറെ ദിവസങ്ങളായി ഉണ്ടായിരുന്നു. അതുകൊണ്ട് തനിക്ക് 10 ദിവസത്തെ അവധി വേണമെന്നായിരുന്നു സന്ദീപിന്റെ ആവശ്യം. അവധി ചോദിച്ചതും CI അധിക്ഷേപിക്കുന്ന തരത്തിൽ പെരുമാറി എന്നാണ് സന്ദീപിന്റെ പ്രധാനപ്പെട്ട പരാതി. അവധി തരാനാകില്ല എന്ന് കടുപ്പിച്ചു പറഞ്ഞപ്പോൾ താൻ മെഡിക്കൽ അവധി എടുത്തോളാം എന്ന് പറഞ്ഞ് സന്ദീപ് പോലീസ് സ്റ്റേഷനിൽ ഇറങ്ങി വരികയായിരുന്നു. ഇറങ്ങി വന്ന സന്ദീപിനെ പിന്തുടർന്ന് സന്ദീപിന്റെ ബൈക്കിന്റെ താക്കോൽ കൈവശപ്പെട്ടു. ഈ സമയത്തൊക്കെ സന്ദീപ് അപ്പോൾ നല്ല മഴ പെയ്താണ്. ഈ മഴയത്ത് നിൽക്കേണ്ട ഒരു സാഹചര്യം പോലും ഉണ്ടായി. തിരുവനന്തപുരത്ത് വലിയ പ്രശ്നമുണ്ടായി. പഞ്ചായത്ത് പ്രസിഡന്റ് ഉൾപ്പെടെയുള്ളത് പോലീസ് സ്റ്റേഷനിലേക്ക് വരേണ്ടി വന്നു. പക്ഷെ അപ്പോഴും CI എന്നാണ് പറഞ്ഞത്. ഒരു തീര പോലീസാണ് എന്ന തരത്തിലുള്ള പ്രയോഗം പോലും CI നടത്തി എന്ന് പറയുന്നു. എന്നാൽ നമ്മൾ രണ്ടുപേരും PSC വേണ്ടി വന്നതാണ്. ഈ ഡെസിഗ്നേഷന്റെ കാര്യത്തിൽ മാത്രമേ വ്യത്യാസമുള്ളൂ എന്ന് സന്ദീപ് തിരിച്ചു പറഞ്ഞു. ഇതോടുകൂടി കൂടുതൽ പ്രകോപനമായി. എന്തായാലും സെൻട്രൽ ബാങ്ക് കൃത്യമായി അന്വേഷിച്ച് റിപ്പോർട്ട് നൽകി. റിപ്പോർട്ടിന്റെ അടിസ്ഥാനത്തിലാണ് പാലക്കാട് SP സംഭവത്തെ കുറിച്ച് അന്വേഷിക്കാൻ നിർദ്ദേശം നൽകിയിരിക്കുന്നത്. ഷൊർണൂർ DSPക്കാണ് അന്വേഷണ ചുമതല. ഈ അന്വേഷണ റിപ്പോർട്ടിന്റെ അടിസ്ഥാനത്തിലായിരിക്കും തുടർ നടപടി ഉണ്ടാവുക. ഇതിന് മുമ്പ് ഒട്ടേറെ പരാതികൾ പോലീസിനകത്തു നിന്ന് മാത്രമല്ല നാട്ടുകാർക്കിടയിൽ പോലും ഉണ്ടായിട്ടുണ്ട്. വളരെ മോശമായി പെരുമാറുന്ന ഒരു സ്വഭാവമാണ് നെല്ലിയാമ്പതിയിലെ CIക്കുള്ളത് എന്നാണ് അവിടുത്തെ നാട്ടുകാർ പറയുന്നത്. അതായത് പാലക്കാട് SP അന്വേഷിച്ച റിപ്പോർട്ട് നൽകാൻ നിർദ്ദേശം നൽകിയിട്ടുണ്ട്. പുറത്തെന്ത് നടപടി ഉണ്ടാകുമെന്നതാണ്
Ordinary Lorentz curve, the to rank the two distribution unambiguously, not only in case of two intersecting Lorentz curve, but also in situations when the dominating Lorentz curve. So it has been seen wherever the Lorentz curve intersect, generally the generalized Lorentz curves may not intersect. So it does mean, and higher generalized Lorentz curve have been seen to associated with the more welfare and less inequality. So generally, so our problem is solved to some extent whenever we have got intersecting Lorentz curve, and moreover, this is also another case. Mean is more in F rather than the mean income in the another distribution G, but the Lorentz curve of F is smaller than this. So this is another important situation. In such case, we have got the generalized Lorentz dominance. We have got the generalized Lorentz dominance as well. And why we should shift is like this. So in literature, there are other important, because I'm going to talk about these in the context of power function. So I just define the Bonfrani curve also. So the Bonfrani curve and associated two measures which have the advantage of being represented graphically in the unit scale and can be related to the Lorentz curve and the Gini index. So Bonfrani curve is given as such. So this is LP upon P. Lorentz curve divided by the P. So actually this this has got the interpretation also. I am just looking at the definitions. So basically it looks at the partial mean. This is the one is related with the partial mean, but interpretation is there. We have got the different papers on these. So I'm just giving the basic definition. This may be defined as the area enclosed by the ordinate axis, the egalitarian line, and the Bonfrani curve. And this is being given by Bonfrani index is just like Gini index, and Bonfrani ordering, and distribution F is said to have the less inequality than the distribution G if and only if Bonfrani curve of F lies above the Bonfrani curve of this, and Bonfrani ordering is same as Lorentz ordering. There is a paper by Pham and Tucken, and it is being discussed there. Another curve is there which is dominance of the Lorentz curve and the related inequality curves in case of power function distribution. So F1 one distribution is said to have less inequality than F2 in the Lorentz sense, if and only if C1 is greater than C2 for the power function distribution. So we are here interpreting that what happens that we can just say that there is a Lorentz dominance or less inequality in the Lorentz sense in case of the power function distribution. It depends upon the parameters C1. So it depends upon the parameter C. So this we say if we have got two parameters C1 and C2, C1 for the F1, then we can just say there is a dominance if and only if C1 is greater than equal to C2. So here we have got this, we have got the C is 3 and where we have got C is 2. So higher this, so higher will be this. And this is some small proof. I think proof is very easy. So this can be easily. So the parameters of the distribution are used to depict the Lorentz inequality as is obvious from the theorem 1 and can be seen from the figure. Figure is also obvious. However, the Lorentz ordering is independent of the scale B, parameter B, and is dependent only on the shape parameter. So this is again the same figure, Lorentz dominance for C1. And now, along with the Lorentz curve, we also have got the concept of the symmetricity of the Lorentz curve. The Lorentz curves, as we have got the distributions which are skew or the symmetric. So here also we have got the Lorentz curve, but symmetricity here we are not defining as in the same sense, but somehow because Lorentz curve lies in the unit scale. So Lorentz curve can either be symmetrical or skewed. If the Lorentz curve is not symmetric, it is skewed either towards 0, 0 or towards 1, 1. So 1, 1 and 0, 0, what are these points? So I will just show in this way. And symmetricity of the Lorentz curve is defined with respect to the diagonal drawn perpendicular to the egalitarian line. So let me just come back. This is my Lorentz curve, and here we have got the 0, 0, 1, 1, 0, 1, 1. So this is a scale. So we just say either it is skewed towards this, or it is skewed towards this, or it is symmetric. So this is being discussed with the help of these diagrams. So there are, you can just see, the PE and P dash F. These are the perpendicular joints. P dash F and PE. These are the two perpendicular joints towards this. This is known as an alternative diagonal, right? And assuming that EG is equal to GF, then we can define the, if EG is equal to G follows, for a symmetric Lorentz curve, PE is equal to P dash F. Both these perpendiculars will be having the same distance in case the Lorentz curve is symmetric. Can also be interpreted in this way. This is symmetric if P mu plus this is 1, this is skewed if P mu plus this is greater than 1, and this is skewed toward 1, 1 if this is less than 1. And in the symmetric curve, this can be noted, the point P mu is on the diagonal perpendicular to the egalitarian line, and if the Lorentz curve is skewed towards 0, 0, the P mu will lie above the alternative diagonal, and this is the positioning and the figure of this. If the Lorentz curve is skewed towards 1, 1, the point will lie below the alternative diagonal, and it has shown that the Lorentz curve in the for log normal distribution is symmetric, and Lorentz curve for parallel distribution is skewed towards 0, 0. And we have shown this result. The Lorentz curve for the power function is skewed towards 1, 1. And this result also follows from the definition of the Lorentz curve for the power function distribution, and taking its differentiation and equating its slope with unity. This leaves you P mu. Taking this P mu and checking this condition P mu for LP mu and limiting value, this comes out to interpretation of this. As is often, Lorentz ordering is independent of the parameter B, while the generalized Lorentz ordering depends both on the C and D. And when B1 is equal to B2, generalized Lorentz ordering depends on parameters K, and it is same as the Lorentz ordering. So, but when one must note, Lorentz ordering implies generalized Lorentz ordering, but reverse is not always true. And similar is the case with the Bonferroni ordering. I just skipped these results, but just want to emphasize that one-fronting ordering is same as Laurent ordering, and it is dependent only on the shape parameter C. And in terms of the comic ordering, there is an interesting result that the results come out to be same as that of the generalized Lorentz ordering. But this in the comic sense, we can say one distribution dominates other if and only if C1 is greater than C2, B1 is greater than equal to B2. And both all these generalized Lorentz and the comic ordering have interpretation in terms of the Rawlsian Laxmian and inequality neutrality approach. These are the welfare criteria of the income inequality, which says we should not prefer only that cake which is higher, which is larger. That is the inequality neutrality approach. And this is Rawlsian Laxmian says we should take that cake where the smallest piece is larger. It means the least well-off person should have the more income. That distribution is always preferred. And these are some results. Laurent ordering is the same as the Bonferroni ordering. Generalized Laurent ordering is same as the comic ordering. And the moments of the Lorentz curve, these are also being derived. And as income distribution may be characterized by its mean and the Lorentz family of inequality measures, even if some of its conventional moments do not exist. And these moments we have defined. These are the kth order moment and D1, D2. These are the certain families of the measures. One is the kth order moments, MK, and Aberge has this, and this is Mehran has defined a class of linear measures, and it is W F inverse P minus mu, LP minus mu, P mu also we can write, and this is a score function, and in particular WP is equal to 2P minus. These score functions different, and this corresponds to the Gini index, which is equivalent to D1, which is the first moment of the distribution, and the choice of the score function also defines certain double. And these are some of the references. So thank you so much. Any questions?
Thank you, Professor Arora, for your wonderful lecture. Very informative. Now the forum is open for discussion to the participants from among the participants. If anyone wants to have any question or doubt or comment. The platform is open for discussion. We have 2 or 3 minutes before we invite the next speaker. Okay, ma'am, there seems to be no questions. So I take this opportunity to thank you for an excellent lecture in this international conference. And I thank Professor Satish Kumar also for giving us this opportunity to be part of this conference. Thank you very much, ma'am.
Thank you, thank you, thank you all. Thank you.
Our next speaker is Professor P.K. Das from the Indian Institute of Foreign Trade. He is a professor at the Indian Institute of Foreign Trade. Welcome, sir, to this second session.
Yes, ma'am, I am here.
I'll just briefly introduce you to the audience. The biodata is very impressive and very lengthy. So kindly excuse me if I skip a few things. Professor P.K. Das, I take pleasure in introducing Professor P.K. Das, professor at the Indian Institute of Foreign Trade. Professor Das completed his PhD in 1996 from the Indian Agricultural Statistics Research Institute, New Delhi. And he has also cleared the NET in 1995. His areas of research include business statistics, business research methods, operations research, statistics and research methodology, quantitative techniques, advanced research methods, advanced data analytics, big data analytics, business forecasting, and financial risk management. He is currently serving the IIFT as a professor of statistics, and his responsibilities include teaching, research, and consultation. He is the head Executive Management Program Division, Kolkata. Before joining this institute, he has worked in various capacities as scientist and senior scientist at the Division of Hydrology and Engineering, Central Soil and Water Conservation Research and Training Institute, Dehradun, Land, Water, Environment and Engineering Research Program, Research Complex for Eastern Region, Patna, Bihar, Directorate of Water Management Research, Patna, Bihar, as Senior Scientist, Directorate of National Academy of Agricultural Research Management, Hyderabad, Andhra Pradesh, as scientist from 1996 to August 1996. He is currently teaching business statistics, business research methods, advanced research methods, and marketing research to different programs of the IIFT. And he has also delivered lectures on application of statistical techniques in training program at Central Soil and Water Conservation Research and Training Institute, Dehradun. Besides this, he has been a financial consultant at the corporate level. He has worked as research analyst and head research division from April 1995 to March 96. He has worked on various research projects. He has completed and is currently working on 3 research projects and has completed 8 research projects funded by ICAR, World Bank, DFID, UK, etc. He has published more than 20 research papers in various national and international journals, authored 5 books, presented more than 23 papers in national and international conferences, and just a minute, sir.
Ma'am, I think you need not to tell all these details. I think it's okay. I think it's a dated CV taken from our website, IFT website, and I would request you to allow me to
Okay, sir.
start the
He has been
presentation.
awarded, he has been a recipient of various awards also. It's a matter of pleasure and honor for us, sir, to introduce you and invite you to deliver your lecture.
Yeah.
Professor Das, sir.
Good morning to all the participants, and good morning, ma'am, in the chair, and also the coordinator and organizers, particularly all the distinguished speakers and participants in this particular conference, students, ladies and gentlemen. It's my great honor and privilege to be part of this particular conference and giving me this opportunity to speak and share the research that we carry out in our institute. So I am also very thankful, ma'am, for giving your kind words and introducing me. I'm working as a professor in Indian Institute of Foreign Trade. Indian Institute of Foreign Trade, we have 4 campuses: Delhi campus, Kolkata campus, Kakinada campus in Andhra Pradesh, and Gift City in Gujarat. So I am based at Kolkata campus of the institute, and I'm a professor in the quantitative techniques area. Now the work that I'm going to present here is, there is a background to it. It started sometime before COVID period, where the government e-marketplace, the B2B portal for all government purchases, the CEO of that portal contacted me and requested that whether we can develop a rating model for the sellers. So they have several thousands of sellers in that portal registered, and it is required, they felt that there has to be a rating model for them. Now, how to develop a rating model is quite challenging, and that was the background, and we started working on that. And this particular discussion is based on that work, and the work is ongoing. Some part we have already published, and some part we are still carrying out and improving. So I will be sharing the PPT. So just give me few seconds. Present now.
PPT share ചെയ്യാൻ പോവാ.
Share window. Okay, let me open that. Yes.
Yeah, can move to the first slide, please.
Yeah, that is what I am trying.
Can this scroll? Or no? Okay.
Click on slideshow.
I think somewhere there is a button which I am.
That you can, that cursor you can move to click on the first slide. Left side you can see.
Yeah, that is what. But somehow it is not moving. Let me do it. Stop sharing and.
Yeah, you use the entire screen.
Yeah, let me start with the beginning and then share. Then share. Yes. So now let me share. Window. Okay, hope you can now see the first slide.
Yeah.
Let me make it. No, let us not make it full screen so that I can. Well, so the title of today's presentation is Enhancing E-commerce Trustworthiness, a data-driven approach to seller ratings using unsupervised algorithms. Well, the problem is that it is not going to the next slide. Stop presenting. What could be the reason? This call is open to anyone. Perhaps I shared the. Let me share the other way. Entire screen. Does it help? Do it from your end. Should I quickly send it to you?
I think
I think that would be better. That would be better. Just it will take a minute. I'm sorry
No,
for
it's
the
okay, sir.
inconvenience. Yes. So reply, and here let me attach this. Yeah, I just shared it. So to your mail ID. So if you could open it and share it from your end.
Professor Satish Kumar, sir?
Yes, ma'am. I will share it from here.
Yeah,
Yeah, that would be great. That would be great.
that will be better.
Now, by the time he shares the slides, let me ask a question to the participants that Did you ever experience something like this, that you ordered a product online, received the packet, and inside the packet you received a slip that please give us 5-star rating and send the screenshot, and you'd be able to find this to other features and how we can derive those features and then develop a comprehensive model, and how to validate that model. We have to keep in mind that we do not have any target here. Do not have any target. We have no other option but to go for unsupervised algorithms. And when we use the unsupervised algorithms, how we can validate the model. The first part of the study, which is already published, discusses the development of the model in details. The second part, which I'm going to present today, discusses addition of one more feature, which is user feedback, and then how to validate this model. And finally, we'll give some recommendation based on our findings. Ratings, that is what is important. Okay, it seems that through customers' feedback. Now in B2C platform, where business to consumers direct platforms, what they do, they take the customer's feedback and then they present that or convert that as 5-star rating, and using that we can understand what is the rating of a particular seller, or sometimes of a driver, or of a movie, or even in trip advisors we can see the hotels ratings, etc. Next please. Now if we use the public procurement theory, now in this particular discussion I would be presenting the background in little greater details, considering that most of the participants here are from statistics background, and I will be avoiding the statistics part. In fact, in B school scenario, and when we present this to the decision makers, they appreciate only non-statistical or non-mathematical part of the presentation, what they can use for decision making. So I prepared that from that perspective, and also keeping in view that the techniques that we have employed are mostly standard, and statisticians are all aware of those techniques. Now, what is important here, that what is public procurement theory? In public procurement theory, they have identified two aspects which arises due to information asymmetry. One is called adverse selection, which happens before I select the seller from where I will procure the or I will have exchange with. That is called adverse selection. And second is, once I select the sellers, then whatever result I get, means whatever product I'm getting or whatever he is providing to me, that is called moral hazards. That means post placing the order. So one is before placing the order, which is adverse selection, and post placing the order is the moral hazards. And there is a need to have transparency in the whole this ordering process and purchase process, inclusivity, efficiency, effectiveness, and accuracy in seller rating. So if we can have a rating which that means a numerical value which can give the, what I must say, the intrinsic value of the seller. Then a buyer can use that value to select the seller by avoiding adverse selection, and also it is expected that the post order consequences, that means moral hazards, will also be less. Next please. Well, so with this background, the flow of presentation, we missed around maybe 5-6 minutes, so I will be little fast. That background and introduction we have discussed. Now, public procurement and importance of seller ratings also just we have introduced. Now, challenges of developing a rating model is, now what approach do we follow? Should we follow the customer's feedback approach? But in public procurement, one is buyer, mostly the government department, which is placing the order. Another is user. Say my office is procuring a laptop computer, and a faculty would be the user of that. So the buyer department will also give the feedback, and the user will also give the feedback. So there are two feedbacks involved. Number one, now whether there is a buyer seller collusion or not, that also we have to take care, and to avoid that collusion. So it is not adequate to use only the buyer feedback or the user feedback. Now, the question is whether the buyer feedback or user feedback can take care all other issues. For example, the reliability, the quality, the timeliness, etc. Is there any correlation between this? And also, if not direct, so we need to see the product moment correlation, and also we need to see the multivariate. That means if these variables are, there is a linear combination of these 5 variables in any form, can there be any relationship? If there is any association, then perhaps we need not to consider all the features. We can consider less number of features, and this multivariate structure can be checked using canonical correlation. So we have to check the product moment correlation, we have to check the canonical correlation, and then we have to finalize the features. Again, while selecting the features, we need to also see that whether the coverage, that means what geographical area the seller is serving. Maybe there is a seller who is sitting in Delhi, and from Delhi he can serve the whole country. Now, there may be another seller who is sitting in a tier 2 city, and perhaps if he takes the third party logistics for serving the whole country, then his other expenditures increases, and being a small seller, perhaps it may not have that much profitability for him. So there is a distinct difference between a large seller and a smaller seller, or the startup seller, and also the original equipment manufacturers like laptop manufacturers, and maybe a small time suppliers who supplies the say office stationaries. So there are issues. So these challenges we have to study diligently and then identify the features. So we review the literature in this, and we find that there are 2-3 approaches to developing this rating models. One approach is direct customers feedback, another could be buyer feedback and user feedback both, another could be incorporating the attributes of the product, another could be the platform repertoire, that also can be included. However, to the best of our knowledge, and that later on was also validated, that transaction level variables was not used to develop the seller ratings so far. So what we have done is we have development, and 2 another segment, and 7 another segment, and 3 third category, PCA third category, there are 4, and all 4 are put in the one segment. So here we find that only 57% is correctly classified, though if we take the bingo classification and one away classification, then we find that it is around 89%, but otherwise it is only 57%. Next, please. So we wanted to visualize this using the TSNE, and TSNE also we found that whatever result we got in PCA, that is, and whatever we are getting through K means, these are akin to each other. So it seems that K means is able to segment the sellers effectively. Next, please. And these are the results regarding whatever hypothesis we set, that we find no association between buyer's feedback and singly delivery time, where p-value is 0.1 and quality p-value is 0.74, and no association between user's feedback and singly delivery time, p-value is 0.37, and reliability p-value is 0.94, and quality p-value is 0.58. And we find no association between users' feedback and a linear combination of delivery time, reliability, and quality based on Wilks test in canonical correlation analysis. So this is very important because we need to consider both transactional variable and feedback variable together. Next, please. Next, please. Yes. So we carry out the visualization, which I have already shown, that the data using the TSNE algorithm, and it reduces the 5 dimensions data of sellers to 2 dimensions that retains original information, and PCA and this k-means that values, when we put it using the TSNE, they are giving similar results. So hence a combination of PCA, k-means and TSNE can be better solution to modeling and visualizing the ratings compared to only PCA or k-means. Next, please. So we conclude that weights of the variables are now we determined using the PCA, and k-means is found to be the most appropriate unsupervised algorithm, and TSNE visualization of 5-dimensional data on 2 dimensions provided distinct groupings akin to 5-star ratings. Display of rating score is recommended here because if we convert it to 5-star rating, then these anomalies, what is happening between k-means and the PCA based presentation, that is due to converting it that score to rating, 5-star rating. So we recommend that rating score, whatever is obtained directly, may be presented, and maybe we used transaction level variables and feedback scores. More transaction level metrics could be identified, and using this, buyers can identify trustworthy sellers, and sellers can improve performance and more sales. That's all. I have one more slide that is regarding the publications and applications. Initial work was published in the International Journal of Consumer Studies, and we wrote a non-technical article in the Hindu Business Line, and 2 portals are using this model. One is Government e-Marketplace GEM in India, and Public Procurement Portal of that is Buy ICT Australia. Thank you so much.
Thank you very much, Professor Das, for your interesting and very informative lecture. We are actually running short of time, but we can take 1 or 2 questions from the audience. Are there any questions for Professor? Okay, then, sir, let me thank you for your wonderful lecture. And
thank you so much, and sorry for the inconvenience regarding the...
No, nothing at all, sir. It has been a pleasure. And over to Satish Kumar, sir.
Yeah, thank you, Professor Das, for your wonderful talk. Thank you. In fact, technically some issues maybe. No problem, Professor. This is usual. We expect that also. But anyway, we have a good lecture from your side, and we are very much thankful to you, Professor. Also, We wish to extend our gratitude to Professor Banu for
Thank you, sir.
sharing.
Thank you very much. It's a pleasure.
Very nice way, in a nice way. And now, once again, thanking you both, and also the other speaker, Sangeeta Arora also was there. And let us give a clap to both the speakers.
Let us clap.
Now, yeah, thanking you all, and let us move to the next session.
Okay, thank you,
Next,
sir.
because we have now 11:55, 5 minutes late. So Professor Ashish Singh is ready to speak, and Professor Gopal is there to chair the session. Now, Bhagyalakshmi.
Yes.
Yeah, Bhagyalakshmi, please introduce the chair and do the needful for the session.
Am I audible?
Yeah. Welcome, Professor.
Hello everyone. We are moving on to the 8th technical session of WSTA 2024, which is a keynote address that shall be shared by Professor G. Gopal. Now, Professor G. Gopal is a professor to the Department of Statistics, University of Madras. His areas of interest include software reliability and advanced statistical analysis. He has a lot of publications to his credit, including a stochastic frontier approach to survival analysis and on the application of Bayesian credibility theory in movie rankings. We feel privileged to have you with us, sir, chairing the session today. On behalf of the organizing committee, I extend a warm welcome to you and kindly request you to take over the session. Over to you, sir.
Thank you. Dr. Satish, our Ashish sir is there.
Thank you, Professor. Thank you.
Professor Ashish is there.
Yeah.
Good morning to every one of you.
Good morning.
I'm thankful. Professor Ashish, good morning, Professor Ashish.
Good morning to you.
Thanks, I am really thankful to the organizers for having invited me to introduce the keynote speaker, Professor Ashish Sengupta. And Professor Ashish Sengupta really needs no introduction. He is well-known statistician, one of the well-known statisticians in India, abroad also. However, formality sake, I introduce him with a brief CV about him. And he is currently consultant at ISI, and he is adjunct professor at Augusta University, Georgia, USA, and he is visiting professor worldwide, including Stanford, one of the prestigious universities in the world. And he has to his credit more than 100 publications. Yeah.
Okay. So let me see.
Yeah.
I have 50 minutes.
Yeah, you can take your own time. And provided people are waiting for lunch also.
No, God,
Yeah.
You have been very, in a way, you have put it in a very nice way. Okay, so I have to rush and finish it also within a reasonable time. So without further ado, so this is the topic of my talk today, the conditionally specified distributions, as you can see, on manifolds. And I have to give allegiance to CSIR because this work has been done as a emeritus scientist of CSIR. So I acknowledge that. And a part of this work later on, as you'll see, is also done with Professor Barry Arnold. That's the later part. I'll come to that. So the approach for this talk would be to introduce you to the area of distributions on manifolds and its applications to what are known as directional data. The motivations or applications are real life problems, like the peak times for diastolic and systolic blood pressure. If you want to look at the joint distribution, so, this would be one peak time would be circular, the other peak time will be circular, and we are talking about the joint distribution. So this will give a distribution on the product manifold of circle cross circle, which is going to be a torus. What is the peak time? Peak time means the time at which that particular variable achieves its maximum. So the peak time for diastolic blood pressure is the time of the day at which the diastolic blood pressure becomes maximum. And you take it for each day. So every day has 24 hours. In this way, you can map the 24 hours to 360 degrees on the circumference of a circle. Each hour is mapped to 15 degrees, and you have a circular distribution. Similarly, it goes for the systolic blood pressure. You have take the time, let's say 11 p.m., at which the blood pressure systolic achieves its maximum. And then you convert this time, 11 p.m., to the angle by looking at the transformation that 24 hours is equivalent to 360 degrees. Every hour is going to be equal to 15 degrees. So if you're looking at the starting point as midnight, then you will have 0 to 15 as going to be equal to midnight to 1 a.m. So the example I was giving you, if 11 p.m. is the time at which your systolic blood pressure achieves its maximum, then with this transformation, it becomes 345 degrees, because the interval 345 to 360 degrees is the last interval containing to 11 p.m. to midnight. So this way that becomes circular. So this joint distribution is the distribution of two circular random variables. Each variable is defined on the space S1, that is of a circle. So the product space is S1 cross S1, which gives rise to the torus. So we're looking at the observations on the surface of a two torus. In the mathematical sense, it's called two torus. Sometimes we loosely call it as a torus. In a higher dimension, it will be hypertorus. The next example is the peak times for the diastolic blood pressure and heart rate. So if you look at the peak time, rather, let me just change this a little bit. Let's say peak time.
So pages, whether it is moving the pages?
I'm going to the motivation, the next page. The second page is motivation.
Okay. Motivation.
That's what I'm talking about. Is it showing up?
Fine, Professor. It is fine. It's fine.
Yeah. Page is titled motivation. I'm going a little slow in the beginning. I'll rush up in the end. Okay. Let me just give you the ideas first, so that people can understand. Then I can go into the mathematics. So the second example is the peak times for dB, which is the diastolic blood pressure. And let's say we take the peak, not that peak times, but just the peak time and the heart rate. So the heart rate is going to be linear. Peak time for diastolic blood pressure would be circular. So this will give a random variable, which is bivariate. So one component is circular, the other component is linear. A joint distribution will be now based on the support S1 cross R1, and which is a product manifold on the cylinder. So the observations will be points on the surface of the cylinder. So similarly, you can talk about circadian rhythms, gait analysis, orthopedic and ophthalmologic surgery, renewable energy. Fascinating usefulness of this type of distribution learns in the emerging area of statistical machine learning, where we'll talk about the both the supervised and unsupervised learning. We won't have scope to do that today, but I'll give you a very simple example at the end to show you the power of this kind of distribution and what it really achieves, how it opens up a new arena, clears up lots of mistakes that could happen if such distributions are not used. Now, the theoretical considerations of the conditionally specified family. What is the conditional specified family? The one whose distribution. The conditional distributions can be more easily envisaged because, let's say, if you're talking about the amount of rainfall and we know the temperature. So, if it is a winter time, we know that the rainfall is not going to be much. Okay, so it will lie between a limited range. But again, if it is in the, let's say, in the summertime, middle of the summertime, when the temperatures are higher up, then we know that the monsoon is approaching. There is a higher chance of rain, and not only that, the amount of rain could be also larger. So that will give you the conditional specification. It is much easily envisaged, and then you can use your Bayesian information, or you can simply use as a statistician your prior information to construct these distributions, rather than looking at the joint distribution of, let's say, temperature and rainfall together, okay, without having any information. That is much more difficult because if you don't know the temperature, if you don't know the conditional temperature, let's say, then the amount of rainfall I was mentioning is much more difficult to envisage and say what is going to be. So this kind of conditional specification really helps you. So highly flexible family for modeling. This conditional specific families are highly flexible, as we'll see, that it can contain the lots of distributions. And one such example is, let's say, bivariate normal. We know that the normal, usual bivariate normal, the conditionals are normal. Okay, each conditional x given y is normal, y given x is normal. But if you look at the entire family, then this bivariate normal distribution that we are familiar with is only one dot in an infinite number of possible distributions, which all of which can be called bivariate normal distributions, and all of which will have conditional distribution of x given y normal and y given x normal. Okay? So that gives a very, very rich family and highly flexible family. In fact, that family of bivariate normal distributions I'm talking about includes the case when the x and y can have zero correlation, but at the same time, the conditionals could be normal, okay, and the marginals could be normal, which is not true for the case of a bivariate normal distribution with rho not equal to zero. Okay, so that leaves you a very flexible distribution which can be used in practice. It's amenable easily to Gibbs sampling because if you know x given y and y given x, then you can use the Gibbs sampler very easily, implement it, get to the chain, and the chain will converge, and you can have a sample from the joint distribution of x and y. So it's an elegant and actually is amenable very easily to Gibbs sampling. Optimal inference can be facilitated by elegant harmonics. I'm not going into the inference part today too much, so I'll skip that. But you can look at the harmonics, look at the representation in terms of the harmonic function, and that will facilitate the inference procedures for this kind of the parameters for this kind of distributions. The challenges are the characterizing the full conditional family. How can we really construct this full conditional? As I said, I know x given y is normal and y given x is normal. Fine. And I know that I can have a bivariate normal distribution which possesses this property. But how can I really characterize all distributions which will possess this property that x given y is normal and y given x is normal? That is, how can I characterize the full conditional family? This becomes a very nice exercise and very interesting exercise in the arena of functional analysis. And today I'll briefly give you a bird's eye view of that part. Okay. So introduction, uh, in that case over here, so in many diverse scientific fields, you'll have these applications, the directions of a flight. So now I'm talking about the circular data first, from which we'll go to the torus and cylinder. And then So in the circular case, we're looking at angles or orientations. This can be in the biological applications in geology, direction of Earth's magnetic field, okay, astrophysics, arrival directions of showers of cosmic rays, meteorology, wind directions, oceanography, medicine. In almost all areas of modern sciences, this emerging data of circular data that we get, these are becoming very important, and the analysis also can be done in this using this modern new emerging technologies and techniques. So what is the difference? Why don't you look only at the usual way of analyzing this data? So look at the simple one, the very basic thing for all statisticians, the mean. So the mean over here is going to be equal to, let's say, uh, yeah, so the mean is going to be equal to, as you see over here, if you look at 15 degrees and 345 degrees, if you take the arithmetic mean, you'll get 180 degrees, which is obviously wrong. So if you look at the definition of the angles, we are really looking at a vector. So what we need to construct is a mean also, but this mean is not the arithmetic mean, but it's a trigonometric mean. And the trigonometric mean, as you know from our high school mathematics, is nothing but corresponding to the direction of the resultant. So that resultant direction is not 180 degrees, but 0 degrees. And hence, if you look at 15 and 345 degrees, the mean that you'll get will actually be equal to 0 degrees, which is the trigonometric mean. Initiating references, these are some books. This is the book supposed to be coming up, hopefully in a few months now. The probability distributions. This is it, Kunio Shimizu, my good friend in Tokyo Institute of Statistical Mathematics. The second one is Barry Arnold, lots of applications and lots of theoretical results also. And one of my old books with Professor Jammala Maraka, which leads the foundations of circular statistics. So this will give you a flavor. Okay, so now let me go on. So the density probability function of a circular random variable is the same as what you would have in the first two cases. Okay, but the last one is the one that includes the periodicity. As you know that if angle is up to 0 to 360 degrees, so 375 degrees actually is nothing but 360 plus 15. So that is modulo 2 pi. And if 375 is equal to nothing but 15 degrees, then the density or any function it defined for the angle should also have this periodic nature, should satisfy this periodicity property. And that is what we're getting at number 3, the periodicity property. So several distributions. Standard one is the circular normal or the von Mises, which looks like the normal distribution. Second one, it gives you the bimodal distribution. Okay, so the bimodal distribution is also in the exponential family. And the third one that you have is one which is not in this exponential family. It's not in the bimodal, but it possesses the very appealing property of having the long tails, also very sharp peak. So for the skewness and kurtosis, especially the financial data, this kind of distributions become very, very useful. So these are come from the stable distribution, and the way that we obtain here is a wrapped stable family. So this wrapped stable family captures high peak, looks at lots of the points of inflection changes, and it also is capable of capturing long tails, heavy tails, fat tails, thin tails. Okay, so it's a very, very highly flexible family. Okay, so let's see. Okay, sorry, so it got stuck somehow. It got hung. So now here is a picture of the torus. That's that one that you have a circle plus circle, the torus manifold, and we have observations on the torus manifold. Okay, so example I was talking about is this circadian clock of gene expression data. We have two sets of genes, one for the liver, one for the heart. We are having the peak times, and we're interested in looking at how the peak times are related, because if you're giving some medicine, then if the medicine is meant for the heart, and instead of that it affects the liver also, then it can create a big problem. So you need to see how these peak times differ. So this hypothesis in this particular case, this is a paper from bioinformatics, they're looking at a 4 to 8 hours delay. If there's not a 4 to 8 hour delay, then the medicine should not be administered if it adversely affects the other particular phenomenon. For example, a medicine for the heart can adversely affect the medicine for the liver if both the peak times happen to come across the same time. So you need some difference in the times in administering this drug. So this medicinal example is what exactly I told you about. So you want to distinguish between them, look at them whether they are synchronized or not. And this will take us to the statistical machine learning aspects. Okay. So now this is the data set and the cylindrical and toroidal models, as I explained. And here, I'm not going to go into the further details of this. We don't have much time. But example vary, as I mentioned, from all areas of modern sciences. The methods of construction are stereographic and inverse projections, Levi-Souto theorem, and then the Maxent characterization. So the conditional specified distributions over here, see the cylindrical model. In this case, we have taken a cylindrical model where the x is given to be normal distribution, and the one that you get in theta is also over here given as the circular variable. So in this particular, very simple example where we have taken the, as you see, the dependence in terms of the normal variable and the circular variable is constructed here. But this is not the full conditional family. We'll go to that construction later on. Toroidal model, similarly, the second one gives you the first one, cosine phi j corresponds to, example, the distribution for the first angle, cosine theta j for the second angle. I stands for, if you have many clusters, then that's what you'll have for the ith cluster. And the dependency is brought in by the second component. Okay, so the problem is with the severity of the normalizing constants, and we'll come to that later on. So the Bayesian approach to this is with the Dirichlet process. And here you can see the nice technique where you have taken a bivariate normal distribution and then wrapped the one component of it. The conditional component is wrapped. So you have specifically conditioned saying that the circle of the part has a mean that depends on the linear variable. Okay, so that's why you see the x coming in there. And x over here is coming in for this conditional variable with the wrapped bivariate Gaussian distribution. The first part is the Gaussian variable. The second part is the variable which corresponds to the wrapped distribution of the circular of the normal distribution. So first part is the normal, second part is the wrapped conditional normal distribution. Together, they define now the components for the bivariate distribution on the over here cylinder, on the cylinder manifold. The pi k theta k gives you the way of statistical machine learning where you'll be doing the clustering, where each of these n theta k are defined in the expression phi. So that is the distribution of the cylinder. So bivariate exponential conditional distributions that we are looking at over here, here is the characterization. If you have exponential family, so this is, please read this as exponential family conditional distribution. If as exponential family members are there, specifically, if I write fx given y as f1 x eta y, because the parameters are going to be functions, eta are going to be functions of y. Similarly, fy given x, please excuse the typo there, it should be y given x. If a y given x in the second expression is f2y, again the parameters tau should be depend on x. So if this f1 and f2 denote members not necessarily of the same dimension parameter, okay, they have different dimensions possible. So if they are like that, then in that case, what you have over here is going to be simply the, yeah, so the distribution that we're looking at, both conditionals are defined now on this particular case where we have over here exponential family member. In this case, it is possible to characterize the whole entire family. Okay, so we have been able to characterize this entire family, and this entire family of distributions that you look at there, is going to be given again very nicely as a member of a bivariate exponential family distribution f of xy. This is a very nice characterization and is given by the Arnold, Strauss, and Casella in their book. And here you have a quantification that given the conditionals are in the exponential family, the full conditional family will be also in a exponential family. And you can also have independence if M curl the matrix becomes equal to 0. Okay. So, but this is the story is only here for the exponential family conditional. So, but this is a very still a very rich one. The result is very useful. So, if I take, for example, a distribution of the torus, you can see the p theta is the distribution. P theta is given 1 cosine theta sine theta. These are the members coming from the circular normal. 1 x square are the members coming from the statistics coming from the normal distribution. Then, if you plug that in the expression f of theta x, you get the family, the full family of distributions on the cylinder whose conditional of x given theta is circular normal and whose conditional theta given x, I mean theta given x is circular normal and x given theta is going to be normal. Okay. Now, but this needs to be extended, as you'll see. This is not sufficient for us because we need to go into the families when the distributions are not going to be in the exponential family, conditional. And as already I gave you the family of snap stable distribution where this is true. And I'll introduce at the end very soon another example where this distribution that you look at also are going to be having a heavy tail, long tail, thick tail, thin tail type of distribution. Okay. And in this case, we cannot use the exponential family. These are members of the Rapp stable family or even some other special or particular family that we are going to define later on. So this particular theorem, the celebrated theorem from functional analysis, where it states that if these are all solutions that we're looking at of this equation fkx gky, where f1, f2, fn are defined by the equation given there, similarly for gy, then these solutions are going to be given by the equation that we have over here, given to be by satisfying this particular constraint. Okay. And the theorem 3 is known as the Axel's theorem as a special case of the Levi-Civita-Souto theorem. Okay, there are 3 very famous probabilists who came across this theorem using this function analysis. As a corollary, we get these solutions that if we can write the solutions of this equation of fix, if we just have this equation, summation fix iy equal to summation gjy psi jx. Note that on both sides we have x and y. But if are functions only of x, phi is function of only of y, similarly g is function only of y, and psi is function of only of x. Okay. If you are able to write it in that fashion, then the systems of mutually linear functions are of the form fx equal to c times psi x. So we can define, we can obtain the f and g given the phi and psi. Okay, if we have this kind of systems of equation, this is again a very useful theorem from functional equation. But all these needs are exercised to come into this arena of this writing, being able to write and put our functional equation in this particular form, so that we can be able to use these results. Okay, so this is a very powerful theorem, and we are going to come back to this later on. So now let me go into the complete family of the generalized distributions. Okay. Oops, sorry. So this is the part I was talking about. This is a part worked with Professor Barry Arnold, where I've been able to characterize the entire family of a family known as the generalized coordinate distribution. As a very quick recap, look at what we're having. Here is the circular normal distribution, exponential alpha cos theta, beta sine theta. And over here, there is a constant that should be coming. It's a proportional to this, in fact, 1.1. So this is one that we're trying to finish up. As you see, the date is April 15th. We're still working on it. So now we can generalize it to what we call a generalized cardioid distribution, where you don't wait into the exponential family anymore. Okay. So the circular normal has the deficiency that is not able to capture the properties of the tails very well. It does not have thick tails or thin tails, and also the peakedness and the points of inflection are not that flexible. So, in order to achieve that and capture those, we want to introduce a new family with the generalized cardioid family. But this family is no longer in the exponential family of the circular normal, naturally because of these deficiencies I told you about. So, going into that, we need to have what we call a power cardioid. The part that you have, if you take gamma equal to 1, is known as a cardioid family of distribution with gamma equal to 1. And with a higher power of gamma, okay, gamma belonging to R, any point in R, it can be negative, positive, this gives the power cardioid distribution. This power cardioid distribution is very flexible, and it is also at the same time is a very rich in its component members of the components. As you see, the 1.3, one that at the f theta that you get 1 plus kappa cosine theta minus mu, this is an alternative representation. It is a symmetric family around theta minus around mu. Okay, but it's not necessarily need to be symmetric. We'll later on generalize it also. So going back to the next one. Okay, let's go into over here, and you can see that this is the condition minus 1 kappa less than 1 and gamma belong to R. So lots of distributions are encompassed in it. Okay, and the generalized cardioid distribution is the one that you first will look at. And we want to say that is it possible to have the generalized cardioid family full conditionals to be characterized? Okay? Because no longer in the exponential family. Can you use the Levi-Civita Axel's theorem? Can you put it in the functional analysis framework and try to exploit those results? How can we do that? Okay, that is the main challenge for us. Okay, so going back to the cylinder model also can be encompassed, as I mentioned, in a similar way, where one can be the generalized cardioid for the circular, and you can take a linear one. Similarly, both of them can be done. And some of this work mentioning on the modeling, and others have come out in a special volume, I think last year. That's the reference to the Sengupta, Shimizu, Ong, and Das, okay, in 2020. On the characterization of distribution. So let's go into the characterization results. Interesting enough. So we'll follow this general one strategy of identifying families. So let's say theta 1 given theta 2, that is theta 2, where is distributed as the GC, this is generalized cardioid. So naturally, the parameters sigma and delta of theta 1 will depend on the conditioning variable theta 2. So I've given sigma theta 2 and delta theta 2. Similarly, for every theta 1 given on 0 to 2 pi, we have the conditional distribution of theta 2 given theta 1. This is again a generalized cardioid, which has the tau naturally depending on the conditioning parameter theta 1, and similarly psi depending on theta 1. We have kept the power gamma as the same. And this is usually done with the stable bivariate, multivariate, stable distribution. And you will note in most of the cases with the Parisian log, this is the one that is gamma is kept fixed. Otherwise, the things simply go out of hand, becomes technically non-amenable to distributions or even inference. So this is one thing that you have to keep in mind. So if you denote this corresponding margin of theta 1 and theta 2, let's put it in this way. So what do we have? So we are going to use our basic statistics. We know that if theta 2 marginal multiplied by its conditional, similarly theta 1 marginal multiplied by its conditional, which gives the joint density. So the equation 3.3 just represents that joint density in terms of gamma. So now we have to do some trick over here. I'll give you a very brief hint of the proof, leave the other determinations later on, but it will give you a flavor of the mathematics involved, and I think you'll enjoy that. So if you use these two equations, again from basic our MStat or MSc or BSc statistics, if you have these two equations, using that F star, just taking the gamma inside, you have F theta 1 to the power of gamma 1 over gamma is that quantity, and G star theta similarly defined. I can write that as F star theta 1 equal into that quantity and G star theta 2 into that quantity as 3.4. Behold that this equation now on the left hand side has both theta 1, theta 2, and right hand side has both theta 2 and theta 1. So we need to put it in a way so that we can have it in the framework of our Axel's and Levi-Civita theorem. To do that, we next define the four functions, all in terms of, let's say, all the theta 1s pulled together and all the theta 2s pooled together. So those the stars indicate the ones that are pooled together. So alpha star theta 1 is f star theta 1 times alpha theta 1. Similarly, beta star theta 2 is the quantity that gives you zeta g star theta 2 times beta theta 2. The important point to note here is that we have pooled the functions together to become functions of a single variable. So the star ones are alpha star, tau star, phi star are only functions of theta 1. Similarly, beta star, sigma star, delta star are only functions of theta 2. Now comes our 3.5. This equation shows that we are able to write it down. Okay, so please ignore the I. This should not be I over here. That is simply the psi star theta 1. Okay, I just is a typographical error. So there are lots of typos here. Unfortunately, this is just paper is being prepared finally. So I didn't get time to check all these typos here. It's still on the under cooking. So anyway, so we have this equation now, and behold that this equation is exactly in the form of Axel's theorem that we had earlier. So using that and using Stefano's Levi-Civita-Soto theorem, we are able to write down that alpha star, tau star, and psi star is given by 3.6. Similarly, beta star, the sigma star and delta star is given by 3.7. So note that we now know the quantities A0, A1, and similarly A21, A22. These are all well defined for us. Okay, these are known to us. So we have been able to find out what is alpha star, tau star, psi star. So, which means we have to go back to the joint density and see how these functions can be put into our actual joint density full form, and will it be a member of the cardioid, generalized cardioid family? That is to say, is it closed under the generalized cardioid family, or have we been able to fully specify the conditional family of the generalized cardioid? So this is the next part. So if you write that down, f theta 2 theta 1 given theta 1, you'll see that this equation to the power gamma, we did the trick over here, and we put in the A0, A1, which are known to us with the parameter vector. Matrix comes in the last line with the f theta 2 given theta 1. It follows that 1 over f theta 1 into that quantity that we have over here to the power gamma. Now, this last part is simply multiplied by f theta 1, so that the f theta 1, theta 2, the joint density is obtained from the conditionals into the marginals, which gives us finally this distribution, which is, lo and behold, again in the generalized cardioid family. So we have been able to prove the closure property and also able to show the completeness property of the generalized cardioid family in terms of defining the full conditional family. So this is a very useful, important family, but we are not done yet, and I'm not going to do that final part here because it is more tricky. But these constants A0, A1, 2, 2, they are not going to be arbitrary constant. They need some constraints so that this density by weight density is a legitimate density. Okay. So, but however, if you take in the univariate case, if you take gamma equal to -1, it corresponds to wrapped Cauchy density or wrapped Cauchy conditionals. Gamma equal to 1 yields cardioid conditionals. So you see, it gives a highly flexible family of distribution. It can capture the wrapped Cauchy, it captures the cardioid conditionals, and then you can have captured the symmetry, and you can go on also looking at long tails and also short tails, whatever you want with the kurtosis. So normalizing constant, I'm going to skip it. This can be in terms of the confluent hypergenetic functions. Skewing can be done. We can now add on the skewing over here. And the skewing, as you can see over here, can be done in various ways. It depends on a couple of papers that my student and myself we have worked on. And this can, by simply changing over here to the second harmonic, 6.3 as you note, introducing kappa to sine 2 theta, going from the first harmonic to the second harmonic. This will give you a highly flexible family of bimodal. And similarly, if you put sine times p of instead of 2, put p there, you will get a p modal skewed distribution. Okay, so I'll skip that and come to the next part now. And this is the last slide. It shows you with the statistical machine learning what we can do. So here we go back to the gene data the phase in the heart and the phase in the liver. We are plotting that. And the plot of the BIs in the heart and liver, we select the number, we did the statistical machine learning to define the cluster. So basically, we'll have over here the four colors: the green, red, black, and blue. Okay, so there are four clusters that you can determine using this toroidal distribution. What is the importance? Why did you have to? Why could you not get just simply use that our bivariate normal distribution? Let's say. Look at the values in red. If you see the values in red are -3. Okay, it stands around the bottom of -3 and then top again as +3 at the two ends of the distribution, because -3 that you have over here point minus 3.14 plus 3.14 is the range from -pi to pi. That is the range. These are the two ends. On the linear scale, these are two ends. Nobody will cluster the points at the two ends to belong in the same cluster. But because 0, minus pi and pi are equivalently 0 and 2 pi are just the same numbers. They are, in fact, the values, let's say minus the degree, 1 degree and 359 degree are very, very close to each other. Similarly, minus 179 degree and plus 179 degree are very, very close to each other. That is why this clustering that you makes total sense. And in fact, this is what it should be. So the red dots that you get are clustered, are put in the same cluster logically and theoretically validated. Okay, this you would not get if you use any bivariate linear distribution or distribution from the R square. So this is one of the uses and importance. Rather than having wrong inference, wrong approaches to our emerging areas of statistical machine learning, this distribution plays a fundamental role. Okay, so these are some of the examples, these are some of the references, and I think I possibly have not overrun. Okay, and thank you very much. Okay, over to you, Chairman, please, sir, please. Hello.
Yes, Professor. Yes. Gopal,
Yes, I
sir.
think I've completed in time, hopefully.
Yeah. Very comfortably you have completed, sir.
Thank you so much.
Okay. Any questions from the audience, please? Audience, please react. Anybody?
I hope I did not put too much material altogether.
Yeah. Sir, I have a few clarifications, sir.
Sure.
Yeah, one is you mentioned about highly flexible family.
Right.
And does it mean only the functional form, or if it is parametric and the number of parameters also?
The highly flexibility means the properties of the distribution.
For the distribution, okay.
Properties of the distribution, which are governed, you are very rightly, as you said, governed by the parameters.
I see. Okay.
So for a normal distribution, if you take mu and sigma, it completely specifies the distribution.
Right.
The distribution is not a member of the regular exponential family.
Right.
As you know, it is a distribution which is Lebesgue measure.
Right.
Measure on also even with x equal to y. Right. So this is Marshall-Organ distribution by weight exponential. So it's not a member of the exponential family. Okay. So what I was talking about, definitely the exponential family. Let's say just a regular exponential family.
Right.
For example, Bashu, block Bashu mod.
Yeah.
So those kind of distributions are in the regular exponential family, and one can try to generalize them to get the full condition. Okay, because theta is x given y exponential in the block Bashu and y given x exponential.
Yeah. And you mentioned about the completeness property.
The completeness property is in terms of the family being able to be able to define or construct a family which will include all distributions for which the conditionals, whatever we are given, is included. Like if I give you x given y is normal and y given x normal, bivariate normal distribution is one distribution, but it's not the complete family.
Okay.
There are hundreds of other distributions which possess the same property that x given y is normal and y given x normal. Can we characterize that family? What are these distributions? Because that is again a highly flexible family. That is what we did in this paper.
Yeah.
We characterize this hundreds of distributions that are encompassed in the same family where x given y is normal, y given x is normal. Or more specifically, x given y is, in our case, von Mises is a circular normal. And theta given phi and phi given theta is circular normal. So it's a distribution of the torus. Similar distributions of the R2 will have the same property. We want to characterize the entire family, which is much,
Okay.
much richer family. The very, very rich family. It's not only the bivariate normal distribution. Okay. I give you an example that correlation of bivariate normal distribution gives you x is equal to 0, then it becomes an independent distribution. Okay. But you have the other distribution where the x given y is normal and y given x is normal, correlation is 0, but still it's not going to be independent. Okay. That is what.
Thank you. Thank you. I understand there is one professor in Bardiyar University. He also is doing some work on circular distributions. I don't know whether he has, sir.
Yeah, I think Bharatiya University, and there are many people. I'm fortunately, when I started off in India, there was no work there absolutely. But I'm so glad to see now so many people in the IITs. Lots of PhDs are coming up, and we have also people. I think Satish's school also doing that down south. We have different Kerala. Lots of people are doing Bharatiya, as you said. Delhi, throughout now it has spread. I think 20 years back or 30 years back when I started this, there's nothing there absolutely. But now I'm so happy that it has picked up.
Okay. Thank you very much. Thank you very much, sir. Thank you very much. Thank you very much. Over to Professor Satish. Over to Professor Satish.
Thank you, Professor.
Thank you. Okay, so I now leave. Okay, so you can share the screen with others. Thanks for all the people who have attended this talk. Thank you for your patience and that will be in this talk. Thank you. I hope you enjoyed it. Thank you.
Yeah. Thank you. Thank you.
Bye, everybody.
Thank you, Professor Ashish, for your wonderful talk. In fact, it is very useful to researchers in the area. The next session, now 12:44, collaborative worker, isn't it?
Yes, sir. Broadly invites Professor for handling this session.
അപ്പുറത്തോട്ടൊക്കെ കയറിക്കോ അത് വയലറ്റ് ഉണ്ട് ഹോൾ ഏഴ്
Am I audible?
Yes.
Yeah. So I am Shubham Nifadkar. Good afternoon, everyone. I will be presenting the joint work with Professor Sivli Mukhopadhyay on behalf of Professor Sivli Mukhopadhyay on multiple response crossover trials. So this is the outline of presentation. So what is a crossover design? Basically, if we have T treatments and we have to allocate them over n subjects in P periods, then such an allocation is known as a crossover design. For example, suppose we have 3 treatments, 1, 2, and 3. And we have 3 periods and 6 subjects are available for this allocation. Then one of the possible crossover design is represented here. Now we consider that corresponding to each subject and in each period, we are measuring responses on more than one variables. So such type of design is called as multi-response crossover design or multivariate crossover design. Various authors have studied multivariate crossover design from the estimation aspects. For example, Dunsmore in 1981 used a multivariate crossover design to measure plasma triglyceride levels at various time points across all the subjects. Grender and Johnson in 1993, they used a crossover design to measure systolic and diastolic blood pressure. So this was a bivariate crossover design, where the responses are like systolic blood pressure and diastolic blood pressure. Grender and Johnson also used a multivariate crossover design or bivariate crossover design, where the responses measured were on the pressure on the right and left eye over all the subjects and in each period. Also, Puta and Chinchilli used a multivariate crossover design to measure blood sugar levels at various time points. We are interested in optimality of a multivariate crossover design. So for a univariate crossover design, universal optimality of these designs have been studied by various authors. For example, Hidayat and Afsarjana, Cheng and Wu, Kunert, and Hidayat and Yang have studied the optimality aspect of balanced uniform design for direct and carryover effects over various subclasses. But they have considered that there is no correlation within the response. Further, Kunert and Martin in 2000 considered that there is a correlation within response variable, and they studied the optimality of an orthogonal array over a class of binary designs. But until now, there is no work on the universal optimality or any kind of optimality for a multivariate crossover design. So, we try to model using fixed effect model the case response variable. The model is given as in equation 1. Here, YDIJK represents the observation from jth subject measured in the ith period on the kth response variable. Mu k is the intercept term for the kth response. Similarly, alpha ik and beta jk are ith period and jth subject effects on the kth response variable. While tau sk and rho sk, these are direct effects and first order carryover effect of treatment S on the kth response variable. And epsilon ijk is the corresponding error term. So we can see that we are the effects, that is the intercept term or period effect, subject effect, these effects are varying according to the responses.
Can you hear
For
me?
our convenience,
Yes.
we write the matrix form where ydk is all responses on the kth response variable and eta, it is a vector of all parameters.
Sadiq sir, start with this session.
Now the model, if we combine all these G responses, then we get the model as given in equation number 2, where ZD is the design matrix and eta is the vector of parameters. So this design matrix ZD is given as IG Kronecker product 1 and P, Z1 and Z2, where Z1 is IG Kronecker product X1, Z2 is IG Kronecker product X2, and X1 consists of the components of design matrix corresponding to period and subject effect, while X2 consists of the components resembling to the direct effect and the first order carryover effects. Now we have assumption that the mean of an error term will be 0 and there will be no carryover effect corresponding to the first period. Further, in order to measure the correlation within response and also between responses, we consider two structures. First one is the proportional structure. So the dispersion matrix of the vector of error terms will be given as this matrix gamma Kronecker product I and Kronecker product V, where V is a positive definite and symmetric matrix. Here we can see that the dispersion corresponding to the first response or between first and second response all will be proportional to each other. So the name is proportional structure. The second structure of the dispersion matrix we consider is generalized Markov type structure. In the literature, this generalized the Markov type structure is partitioned as sigma 11, sigma 12, sigma 21 and sigma 22. Due to the symmetricity of sigma, sigma 12 should be equal to sigma 21 transpose Also, sigma 1 1 will be iron Kronecker product V1. The expression is given in the slides. Here we have two matrices. This structure is dependent only on two matrices, V1 and V is basically a positive definite matrix and a symmetric matrix, while VR should be a known correlation matrix. In order to study the optimality of crossover design, we require the information matrices. So let CDS1 be the information matrix for direct effects under the proportional structure, and CDS2 will be the information matrix for direct effects under generalized Markov type structure. We consider the class of designs or a class of computing designs to be a class of binary designs. Here, by binary designs, we mean that any design where corresponding to each subject, a treatment is allocated at most once. Now, under the proportional structure, we obtain the structure of information matrix for direct effects. It is given as this matrix of gammas inverse Kronecker product CD uni.
Unimash.
Here CD uni represents the information
can you hear
matrix
me?
in the univariate response case, which is represented as C11 minus C12 into C22 generalized inverse into C21. The expressions of all these components is expressed here.
Camera on.
Here we should note that the TD and FT are the components corresponding to direct and the carryover effects in the design matrix. Now, in the literature for the univariate response case, the optimality under the correlation structure has been obtained for orthogonal array of type 1. So, what is orthogonal array of type 1? Now, any design is a kind of array. So, if we pick any 2 cross V subarray, that is any two rows of this array, and then count all the ordered two tuples, so they will be t into t minus 1 in number. Now, if they occur equally often, then such a design is called as orthogonal array of type 1. So, under the multivariate response case, we obtain that this matrix will not be a completely symmetric matrix for orthogonal array of type 1. So, what is a completely symmetric matrix? So, completely symmetric matrix is a matrix whose all diagonal elements are equal and all the off diagonal elements are also equal.
Now, can you hear me?
Now, the universal optimality can be studied if we have a completely symmetric matrix. So this is a result by Giffen in 1975. So we can't use this result. Further, there is another result by Ye in 1986. Which
Sir, Unimash is actually some technical problem. Some problem related with the Bluetooth.
You can see that this sufficient condition also fails.
My talk and
so we resort for an efficient design.
Mash, can you hear me?
In this theorem, we obtain that an orthogonal array of type 1 and strength 2 will be an efficient design for direct effects over a class of binary designs for the multivariate setup. So the difference between univariate and multivariate setup will be that the orthogonal array has attained universal optimality in the univariate case, while in the multivariate case, it fails to attain universal optimality. But under the proportional structure, it is still an efficient design. Now, under the generalized Markov type structure, in this theorem, we obtain the structure of the information matrix for direct effects for this multivariate setup. It is given as n upon t minus 1 into the matrix which is partitioned as lambda 1, lambda 2, again lambda 2 and lambda 4. The expressions of lambda 1, lambda 2 and lambda 4 are given here. We can see that the difference between proportional and generalized Markov type structure lies it's in complexity. Like the expression for the information matrix itself is more complex than the proportional structure. Now, again, in the generalized Markov type structure, under this bivariate setup also, the information matrix CD star is not a completely symmetric matrix. Also, the sufficient conditions provided by Ye in 1986 fails. So we have to resort for an efficient design. In order to obtain in order to check whether this orthogonal array of type 1 will be efficient or not, we first obtain the upper bound of trace of the information matrix. Here, we consider designs which are binary designs. So in this equation number 6, we obtain the upper bound for trace of CDS2. In the next remark, we see that any orthogonal array of type 1 and strength 2 will attain this upper bound if and only if this condition is satisfied. The condition is that trace of V1 star Xi matrix into trace of H Xi transpose VR star Xi should be equal to trace of VR star Xi into trace of H Xi transpose V1 star Xi. Now, as we have seen that the structure of information matrix or even the dispersion matrix sigma depends on the structure of V1 and VR. So for V1 and VR, we consider following choices. These are like Matten 0.5, Matten 1.5, and Matten infinity. Here Matten 0.5 corresponds to a AR1 structure, while Mat infinity, this is corresponding to a Gaussian structure. Here R1 basically is the correlation or a correlation measure within responses. So we consider 7 cases depending on the choices of V1 and VR. And now we consider the relative difference for any design D0. This relative difference is between the trace of the information matrix corresponding to the design D0 and the upper bound, which we have obtained earlier. Further, there are two components, sigma 11 and sigma 22, which are constants. So in remark 4, we see that for any binary design, whenever sigma 11 will be equal to sigma 22, this relative difference will be independent of their values. So we consider few designs for illustration. For P equal to T equal to 3 case, we consider an orthogonal array which is given by D star and a uniform design which is given by D1. Here we do not consider balanced uniform design because for P equal to T equal to 3 case, a uniform design is a balanced uniform design only. While when the period and treatments are equal to 4, we consider 3 designs, D1, D2 and D star. Here D1 is a uniform design, D2 is a balanced uniform design, and D star is an orthogonal array of type 1 and strength 2. So, for our illustration, we consider sigma 11 equal to sigma 22 so that the relative difference value will be independent of this sigma 11 and sigma 22. Further, we plot the minimum value of the relative difference and the maximum value of relative difference for uniform design, balanced uniform design, and orthogonal array. This minimum and maximum are considered over the values of rho. Here, this rho is a correlation or it induces correlation between responses. Now, why we require two values? Sorry. Yeah. So why we require this minimum and maximum? So minimum is required to check whether D not attains the upper bound U or not. the expression of u was obtained earlier in equation number 6. And the maximum value of relative difference is required to check how far at most this stress will be from the upper bound. So lower values of this maximum value of relative difference is a better condition. And in case if it attains, then we call it as a efficient design. So in this plot, we consider a few cases, basically case 1 and case 2 for the minimum and maximum value of relative difference. Further in this plot, we consider case 3 and case 4. And here we consider the other cases, that is case 5, case 6 and case 7. These are for p equal to t equal to 3 case. In all these plots, we can see that the orthogonal array, the minimum value of relative difference and the maximum value of relative difference is very close to 0. While corresponding to the uniform design or a balanced uniform design, this minimum value and maximum value is too far. In some cases, it almost close to 100. Further, we consider p equal to t equal to 4 case. So here we will have three designs: uniform design and orthogonal array, which are represented respectively as d1, d2, and d star. Here also we can see that for an orthogonal array, the minimum and maximum relative difference are almost close to 0. In the graph, due to the scaling, it may appear that they are equal to 0, but when we check the theoretical values, it is not exactly 0. It is not attaining the upper bound.
Dear chair mentioned that, so this is a joint work with a Professor Elisbar Nadaraya. He is head of the Department of Probability Theory and Mathematical Statistics at Tbilisi State University. And so this is a continuation of our works about the Bernoulli regression function. So we have a series of works related to the investigation of the Bernoulli regression function. And now we just introduce a new non-parametric estimate for a Poisson regression function. In this work, so the limiting distribution of the integral square deviation of the non-parametric kernel type of estimate for Poisson regression function is established. Then the test of the hypothesis testing about the Poisson regression function is constructed. And then so we investigated the consistency of the constructed test, and then also they investigated the power asymptotic of the constructed test. So let's start the introducing and formulating the problem. So let's introduce the random variable y, which takes the values 0, 1, 2, and etc. with the probabilities lambda to the power of k over k factorial times e to the minus lambda, where lambda is positive. So this is a well-known Poisson random variable, and so k changes from 0, 1, and etc. We assume that the parameter lambda is a function of independent variable x, where x changes from 0 to 1. So if we rewrite now the distribution of y in terms of lambda x, so it's same as y equals k equals lambda x to the power of k over k factorial times e to the power of minus lambda x. Here, the important is what? Lambda x is known as a Poisson regression function. And so this is introduced in a cited paper 1, paper 2. Now I will show these two papers briefly. So this is a paper 1. So this is a Efremovich monography, and then Kohler and Krysiak's article about the confidence interval for the Poisson regression function. Let's continue this. So as I mentioned, lambda x is a Poisson regression function. So now we're considering the division points of the interval 0, 1, and let's denote this division point as xi changes from 1 to n, etc. up to n, and let's take this by the equality 2i minus 1 over 2n, and I changes from 1 to n. Let's further consider yi be independent Poisson random variables with this distribution. What is the problem? The problem consists in estimating the function lambda x, where x belongs to 0, 1, based on sample. So I will repeat again. So the problem is to estimate lambda x, which is just this lambda x, which is a Poisson regression function based on sample y1, y2, and etc., yn, and all these are Poisson random variables. So therefore, we want to estimate lambda x regression function based on the sample. So such kind of problems arises in medicine. Here it's cited paper 3 and 4. In astrophysics, it's indicated in cited work 5, and etc. For us as a mathematicians, important is to estimate and investigate the property of lambda x, states its statistical significance, and then creating the hypothesis testing and the related questions. But of course, here it's mentioned, it has a lot of applications, but so this is be honest, is a theoretical work. As an estimator for lambda x, we are introducing the following statistics. Lambda n hat x, which is a ratio of these two expressions, lambda 1 n x and lambda 2 n x. What is lambda 1x? Lambda 1x is just the case when we are plugging here instead of nu in second, instead of nu 1, we are getting 1 over nbn, then sigma k x minus xi bn and yi. And the second will be only the deterministic part because y will be to the power of 0. So therefore, this estimate is just a ratio of random component and the deterministic component. So it's a well-known, this is a Nadaraya estimate, Nadaraya-Watson's type estimate, similar to this. And this is just a very popular estimator, which introduced the Professor Nadaraya some years ago. And just based on this estimate, we're assessing this lambda x. Let's formulate some conditions which we need for proving the main results. Here, the kx is a distribution density, which satisfying some of the requirements, which we formulate in what follows. Bn is a sequence of numbers tending to 0, positive numbers. So the kx is a kernel positive is chosen so that it is a function with a finite variation and satisfies these conditions. And so the kx equals k minus x, so it's even, it's equals to 0 outside of the interval minus tau tau, and then integral on the whole domain equals to 1. And such kind functions, so the class or set such kind functions, for simplicity, we will denote as h tau. Let's see I denote the class of the functions Lx having bounded derivatives up to order I. Also, let's introduce the following notation. Tn bar will be the following statistics nbn, then integral on omega n tau. Under the integral, we have just lambda 1x minus mathematical expectation of lambda 1 nx squared dx. And so if we look, this is just the case when instead of variable here is plugged 1. So this is a random component, yeah? So the domain you can see is tau and omega. So it's inside of the interval 0, 1 because for avoiding the boundary effect. So it's more than 0 and less than 1. So this is a CK, FK is a martingale difference. Second is a asymptotic representative if KX, so the kernel belongs to the class which we introduced, and LX is a function with a bounded variation, and if NBN tends to infinity, then such kind of limiting relationship is stated uniformly in X and Y belonging to 0, 1. So the proof of this lemma is given here, is cited. Then the lemma 3 is also the technical lemma. If kx belongs to h tau and lambda x belongs to a C1 class, if nbn square tends to infinity, then the variance sigma n square of nbn have a limit which is sigma square lambda and which equals to this, where delta n equals to the mathematical expectation of the statistics Tn bar, and in this statistics, so the main part and then asymptotical part is given, and then delta lambda equals to this. I will omit the proving of this because it's quite technical proofs. So then the main theorem is formulated. So this is the main theorem, and in this main theorem, we are stating the limiting distribution. Let kx belongs to h tau and lambda x belongs to the C1. So if kx belongs to this and lambda x belongs to this class, and nbn square tends to infinity, then such kind limiting statement is true. What does it mean? This it means that so the Tn bar minus delta lambda over sigma lambda times root from Bn tends to the standard normal distribution. And so it means that the convergence in distribution. So this where in this theorem, delta lambda and sigma lambda are just defined in a lemma 3, as I mentioned. So this is a delta n, and this is a sigma square lambda, sigma n square. All these are given here. So this is one of the main theorems. So proving also I will omit. So the proof of this theorem is based on the techniques which is developed by Professor Nadavaya. And so in all our works, we are using this technique. So this is one of the techniques. It's based on the Lipser-Shirev's well-known fact about the martingale difference. And then this is just the conditions. Theorem requires the fulfillment of these conditions of this theorem. So this is 5 pages long proof. I will omit this. Okay, then this theorem we can apply for proving the second important theorem. This is a theorem 2. What is given in this theorem? If kx belongs to the same h tau class and lambda x belongs to C2, moreover, if nbn square again tends to infinity and nbn4 tends to 0, then we have a next following the limiting relationship, but now it's stated for the main statistics Tn. I will show you again and I will remind you which statistics is Tn. So as I introduced this at the beginning, so this is a Tn and this is a Tn bar. Okay, let's to continue the formulating this theorem. Then Tn minus delta lambda over sigma lambda times root from Bn again tends to the standard normal distribution. So here again the convergence by the meaning of distribution. So here the main idea of the proving of the theorem is what? So this statistics Tn is represented in terms of statistics Tn bar, and then the other two remaining terms. And then again, the proving is based on the same techniques. Next is applying this theorem. So the theorem 2 gives us possibility to construct the test of the asymptotic level alpha, where alpha changes alpha from 0 to 1, for the testing hypothesis H0, according to which we are checking the hypothesis when lambda x equals to the lambda 0x. So I want to repeat again. So the theorem 2 give us possibility to construct the test for which or based on which we are checking this hypothesis. So the critical region is stated by the inequality theory. Tn is more than or equal Qn alpha. So this is a critical region. Then all parameters here, Q alpha is equals delta lambda sub 0 plus lambda alpha root from Bn times sigma lambda sub 0. All these are defined here. Now is the question, investigate the asymptotic property of this test. Or what does it mean, this behavior of the power of the function when n tends to 0, tends to infinity. And in first place, we consider the question of whether the test is consistent. And the following answer to this question is the following theorem. Theorem 3. Let all conditions of the theorem 2 be fulfillment. Then, as n tends to infinity, so the limiting power is 1. So the power of the constructed test tends to 1. Which means the test defined up this test is consistent against any alternatives of the form where lambda x is different from lambda sub 0x. So this is a proof of this. I will omit. Now look, thus for any fixed alternative, the power of the test based on Tn tends to 1. However, if with a change of n, the alternative changes converging to the basic hypothesis, then the power of the test will no longer necessarily converge to 1. And so let's bring example of this. So an example of this is if we consider the sequence of a Pitman type alternatives which are close to the basic hypothesis, and if they are H1, where lambda 1 and x equals to the lambda sub 0x plus gamma n phi x plus O small gamma n gamma n tends to 0. As you see, this is an alternative which is close to the basic, because the limit of this is lambda sub 0x, but now we will see that for such kind of alternatives, so this test power will not necessarily tend to 1. And the answer on this is just the theorem 4. Let lambda sub 0x phi x tends to C2 class, and kx belongs to the H town. If, let's consider Bn be n to the power of minus delta, and gamma n be the n to the power of minus 1 over 2 plus delta over 4, where delta changes from 1 over 4 to 1 over 2, then statistics, which is a Tn minus delta lambda sub 0 over sigma lambda times root from Bn for any alternative of the type 31 has a distribution in limit this, which is normally with the parameters. Look, 1 over sigma lambda sub 0 integral from 0 to 1 phi square x dx and 1. But the power of this test equals to this expression. What can we state from this? We can see that so this power does not 10 to 1. But as you see, if we consider the alternatives of the form, Pitman's type, so we are saying that so it's not always obligatory the limiting power tending to 1. So this is a proof of the theorem. Now, a few words about the remark. It should be emphasized, and I mentioned about this at the beginning. Lambda and hat x behaves worse near the boundary of the interval 0, 1. So therefore, we are considering the interval, which is different from 1 and 0. Then, for avoiding the boundary effect, so the I mentioned so the proof of theorem 1 and 2. So it's our techniques which we developed in our papers 10 and 11. Then the idea of proof of theorem 1 is analogous of the theorem of 1 from paper 12. And remark 3 is xib is the division point of the interval 0, 1 chosen. So say h of x is 2k minus 1 over 2n, where hx equals to the interval from 0 to x, hu, where hu is some non-continuous function with a density on 0, 1. So then arguing analogously to the above, we can obtain the generalization of this paper, result of this paper. So if we consider the another division point like this, so we can generalize this result. What is the reference? I mentioned, so this is Efremovich, Koffler, Shim and Tran, Avitan, Kolzak. So this is a well-known Mandaraya's work on regression estimate. Then Watson's smooth regression analysis, and then 8 is our common work. Then this is a Lipzer-Shirev's work, which we used in theorem. Then Hart and Worley, the kernel regression. Nadaraya, again, here is his monograph. And our last 12th paper is again our common work. So this is briefly about representing our results related to the Poisson regression.
And Bayes estimator under the line X loss function, Bayes estimator and the G estimator
Questions?
for the general entropy loss function.
So,
These
here
are
we
the
define our
mathematical
lambda x
calculations.
on the
And
interval 0,
but
1.
the posterior
Implies that
expression,
the
these
interval
are the
0, 1 if you
posterior expression
define
for the
on any
parameter
finite
alpha
interval,
and the parameter
means
lambda,
it's the Lebesgue
because
function
the
is finite.
posterior distribution
As I understood, what will happen?
So,
You are
but
asking about
these
the
posterior are
different
not in
interval from
closed
0
form.
to 1?
So we are going to the
0 to 1.
computational techniques
Yes,
using
it's
the Markov
by
chain
simple
Monte Carlo
transformation.
technique to
We can
generate the
transform
posterior
this on
sample,
any
and then we
interval of
have to
AB.
give the ideas about all these
But for
statistical
simplicity,
inferences under the Bayesian
we are
paradigm.
considering from 0
But
to 1. But
the
it will
another
be very simple to
E Bayesian
formulate everything
estimation is
in
the
terms of AB.
new of the fashions and new of the paradigms
Any other
developed
questions?
developed in 1997, and then popularized very much for introducing
no
the
questions. Thank you, Professor, for the informative session.
introducing the
Thank
priors.
you.
There are 3 types of the prior has introduced in here for
So
the
thank you,
model, for
Professor
the
Shibu
increasing
sir,
and for the increasing
for chairing the
time.
session.
This
On
way,
behalf of the
and
organizing
these are the
committee,
mathematical
I
calculation,
express my sincere
and
gratitude
then
to you, sir,
also the
and
posterior
the
samples
speakers
are
also.
generated using the Markov chain Monte Carlo algorithm. This is the Markov chain Monte
I
Carlo
want to say
algorithm,
one more time,
and
thank you
in
for
the there is
providing us with the
samples
opportunity
generated, and
for
using the
collaboration, for
proposal of
communicating.
the
So you
estimated
are
normal population,
all year,
and using this
last years
algorithm to
holding
obtain the
this
posterior
conference, and
samples,
so thank
and
you for
based on
this.
this posterior sample obtain the Bayes estimates. For the performance of the estimators, for long run, whether the performance is proposed estimator is performing well or not, to be justified
Sorry, sir,
for the
this session is now over.
numericals, this choice of the values n is equal to 30, and M is the effective sample size with a step of 10 to 25, a step 5
Okay,
increment.
thank you,
And is
Professor.
equal to, these are the choice. For this choice, proposed estimators
Just a
are
minute.
performing here. Here, n is the number of sample size and obtain the risk of the estimators for alpha hat under these are the estimators. This is the Bayes estimator, this is the E-Bayes estimators, and this is the E-Bayes estimator. For the three types of the estimators were proposed in the E-Bayes estimator for the prior choice of the prior.
So, Mr. Manoj,
Yes, ma'am.
you
Yes,
have
ma'am.
മറ്റേടത്ത് എന്ത് പറ്റിയെന്ന് നോക്കാവോ? മെയിൻ ഹോൾ മെയിൻ ഹോൾ
What about here? I think thank you, Professor Professor Peter Bubbly, and Professor Nadraya, and Shubham Nibarkar for your nice presentations. And also we wish to thank our chair, Professor. Hello, can you hear me? Hello?
കഴിഞ്ഞു, എല്ലാരും പോയെന്ന്.
Okay. Thank you all. Those who have interest to join the other sessions, the session B is also running now. Can join there.
Ah. Hmm.